Humans are kept as pets. The Fantastic Planet. 3 science fiction classics. Saturdays starting at 8 p.m. on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Throughout the ages, we have looked at the night sky and wondered. This fascination is still with us, filling today's astronomers with questions. Do solar systems like our own circle distant stars? Do black holes beat in the hearts of galaxies? Is all that we see only a small fraction of all that is? Armed with technology, astronomers see deeper and explore farther than ever before. Questions that have long remained out of reach are nearly in their grasp. This 6-part series follows astronomers to all regions of the globe. They will take us to the edge of our knowledge of the universe, on a search for answers to perplexing mysteries.
I get a big kick out of the fact that we build a machine that can see the light coming from the beginning of the universe, and that's a lot of fun.
Astronomy is a very fascinating subject, but maybe the most interesting thing is that we cannot even imagine the kind of new events, the kind of new phenomena which we can discover.
Astronomers do astronomy for different reasons. I personally am just interested in how everything came about, and in particular how we came about.
My interest in astronomy started from these questions like where does the universe come from and where is it going to go?
The greatest product of astronomy is the learning about new ways of perceiving, new ways of thinking. Astronomy is for the soul.
I think what astronomy brings to society is something enduring. Maybe more enduring than architecture, than art, things like that. What we bring is the truth about who we are, what we are, where we came from, and maybe even whether we have company out among the stars.
Adventure into the unknown with the Astronomers, next. The night is full of sparkling things, things that glitter in crystalline brilliance, things that dazzle the eye of whoever takes the time to look up and wonder.
The moon, the whole moon, and nothing but the moon.
John Dobson,
I've got it on the crater T.
Carney Barker for the Cosmos, Pitchman for the Stars.
These are all North streamers for that crater. Yeah, they're all from me.
Dobson calls himself a sidewalk astronomer. He wants the world to see and to wonder.
Telescope as big as those over there. Come see the moon. Come see the moon. Did she see?
Him, yeah.
Oh, him?
I could see the craters on the moon, and I'd never seen that before, and it was exciting. molto bello, beautiful.
Yeah, I can almost touch it.
Come see the moon. We're looking at the moon through the telescopes.
Everybody is born curious. Everybody wants to see this universe. Everybody wants to understand this universe. They're just waiting for somebody to present it to them. Everybody wants to understand this thing in his guts.
Astronomy is an endless quest into a universe of untold depths and mystery.
Come see the sunspots.
Astronomers have always gone to where the light is.
The big green ball is the sun, the whole sun, nothing but the sun.
Dobson goes to where the people are.
And the spot that you see on my side, that's big, a little bigger than the Earth. The sun's spinning from my side to yours. Now, if there were 1 million amateur astronomers with telescopes, and they were willing to let a few thousand people each look through their telescopes, there would be a chance for all the people in this world who wanted to see, to see.
The whole thing is the sun.
The whole thing is the sun.
Dobson was once a chemist, then a monk. Now he's a teacher, helping to rekindle curiosity.
Well, thank you.
Don't thank me. It's your son. Come see the sun.
Is this a study that you're doing? Or...
No, this is a study that you're doing. Have a look.
Oh, okay, I'll look.
Now, the big green ball that you see is the
Dobson
sun.
builds his own telescopes. This one he designed to safely view the sun.
And then after that, we run it through a welder's glass in here. That's what makes it green.
Oh, okay.
You can't see a big green ball in there? Hang on. Now, the fact is that the parks already have the best seeing conditions. And so if we're going to get the telescopes to where the public is associated with the best seeing conditions, we have to do it in the national parks.
There's no green sun.
What? No, the sun isn't green, but it looks green in here because we have a welder's glass in here. But that big green ball is the sun. Look again. That big green ball is the sun, okay? And those dark spots that you see are on the sun. And they're bigger than the Earth. They're bigger than Crater Lake. They're bigger than Oregon. There's something inside you that drives you to understand this universe. It's not something you have to think about. There's something that drives you to understand how things work and how the universe goes, why we see what we see. Why is it like this? Why isn't it some other way? Why isn't the universe made out of butter? Why does it have to be made out of these little tiny things that you can't cut up any further? The spot on my side is a little bigger than the Earth, and it just came around from the other side of the sun by the spin of the sun. I used to wheel that telescope around the streets, and then some kid would say, "What's that?" And I'd say, "It's a telescope. Do you want to borrow it?" Well, of course he wants to borrow it. And then we'd put the telescope in some kid's garage, and then I'd sneak away from the monastery at night and come over and shoot off my trap at the eyepiece, like we do here, so that the people could understand what they see. Well, some of those kids, you see, who looked through that telescope wanted to make telescopes of their own. And I thought, oh, Lord, if I help those kids make telescopes, I'm sure to get thrown out of this monastery. So I got thrown out of the monastery.
To Dobson, a telescope is a means to an end, a tool for people to connect with the universe and begin to understand it.
To see the universe is one thing, and to understand what you see is quite a different thing. And so we try to get them to see a slideshow, and so you can talk about what's the whole thing all about, what's the universe made of, on what kind of energy does it run, like that. Physics is about the behavior of matter.
Nighttime is when Dobson really shines. Before unveiling his telescopes, he teases their minds with questions. He calls this a star party, the only price of admission, curiosity.
You can ask any kind of embarrassing question. As I said, if I don't want to answer, I won't have to answer. Yes?
I'm wondering about these black clouds you can't see stars beyond.
Those are the kind of things that you're sitting on. You're sitting on one of those clouds. The universe has 3 ingredients: hydrogen and helium and the dust of exploded stars. And the Earth is made of the dust of exploded stars.
To Dobson, astronomy is the people science. The universe lies open to all. Everyone can learn how it works, how it began, how it's expanding, and how we have come to know it.
All the distant things are shifted toward the red, and we usually understand that to mean that they're going away. Now, the big problem was, why are they all going away? So the simplest explanation was that there was a big explosion called the Big Bang. You must have heard of it. The Big Bang. And because of that, all the distant things are going away. But we like to show you samples of these different kinds of things. Gaseous envelopes around old stars, the clouds from exploded stars. We like to show you all these different kinds of things and some planets.
A clear night, people eager to see. Dobson asks for nothing more.
The Cheerio or the Fruit Loop before. Now we want to get M13. M13 is a globular cluster. This is a public star party. This is in a national park, and this is where we take the telescope so that the general public can see these things, which they can't see other places. And what we try to do is to show the bright objects, the important objects if you want. Okay, please climb fast like a chimpanzee. You'll see the thing drifting in from the upper left, and it'll drift across to the lower right, but you'll come down long before that so that the other people can see. You'll see Saturn to the upper right. It'll look like a straw hat. It takes light 1.5 hours to come from Saturn.
For centuries, astronomers studied only what could be seen. Aided by technology, they now see what before had been invisible. Visible light is only one way to investigate the universe. Astronomers now use the entire spectrum of radiation. But these investigations have revealed a mystery that lies beyond all these ways of seeing. There is a dark side to our universe. Most of the cosmos is made of something astronomers cannot see at all. Dark matter. Vera Rubin is an astronomer at the Carnegie Institution of Washington. She played a key role in the discovery of dark matter. It was natural curiosity that fueled her desire to become a scientist.
I started looking at the sky probably at age 10 to 12. I just got hooked on watching the stars. Within a short period of time, I really got more interested in watching the sky than in going to sleep. So I went to the library, read books, built a little telescope, and just decided I wanted to be an astronomer. I had a physics professor in high school who didn't really know how to relate to a young girl who was interested in science. When I finally went up to him and told him I was going to college on a scholarship, he said, well, you should do all right as long as you stay away from science.
Rubin became an astronomer, specializing in galaxies. Her work led to the startling discovery that most of the matter in galaxies has some dark form that we cannot see.
I mean, ideally, what we all dream of is that when you do when you ask questions in science, when you ask questions of nature, you will get answers that are much bigger than what you went out to find. I mean, it may raise enormous questions, which this has done, but also it made other little puzzles fall into place. And the combination of those things really is a very rewarding result from any study.
Rubin studied starlight captured on glass plates called spectrograms, patterns which revealed the motions of galaxies. A galaxy consists of stars and gas bound together by gravity. Astronomers had assumed that most of a galaxy's gravitational force comes from the luminous center, where most of the stars reside. If this was so, stars close to the center would orbit more rapidly than those farther out. But this was not what Rubin found. By analyzing the spectra, she determined that stars in the outer regions were moving nearly as fast as those closer in. If gravity came only from the luminous regions, stars moving this rapidly could not stay in orbit. The galaxy would fly apart. The conclusion seemed inescapable. Galaxies are held together by an invisible halo of dark matter.
I was really interested in learning something about the way the galaxies were made, were put together, how their mass was distributed. But I was not smart enough to think I was looking for mass, which we don't see. What's missing is the luminosity. So we know there is mass there. So a better name might have been the missing luminosity. That is, where is this matter? Dark matter is a good term. Unknown matter may be a good term, but the fact that it's dark is its most prominent characteristic. I like dark matter. In a galaxy, it looks like most of the light is at the center, and therefore we had expected that most of the mass would be at the center. And just like in the solar system, where most of the mass is at the sun, you expect that as things get farther and farther away, they orbit more slowly. And what we found is that these stars are going just as rapidly as those stars, and we're forced to conclude that they're responding to a gravitational field we don't see. And that gravitational field must be composed of dark matter. The universe that we saw with our eyes and our telescopes, and even our radio telescopes and infrared telescopes, was only a very small fraction of the total universe. That when we look at stars and galaxies, we're only seeing 5 or 10% of what's there. And so the significance is that it really raises the question as to what the rest of the matter in the universe is and what it's like. I mean, you can dream up anything if you have 90% of the mass of the universe to play with. So the job of astronomers, certainly the job of observers in the next generation, is to try and figure out how to get a handle on what this dark matter really is.
Well, it's quite possible, in fact very probable, that the dark matter actually controls the fate of our universe, in the sense that it appears there's so much of it around that it dominates the gravity of ordinary systems. You know, astronomy is biased towards things that glow in the dark, and it's sort of amazing to think that when you look out at the night sky that there might be 10 or 50 times as much stuff out there that you really don't see, that in fact is controlling the fate of stars and galaxies and the universe as a whole.
Tony Tyson is an astronomer from Bell Laboratories. He's a leader in the search for dark matter. Tyson's work requires the use of the world's largest telescopes. That means traveling to distant observatories. Like many of today's astronomers, Tyson began his career as a physicist.
Studying the universe is basically physics. The question we want to answer is the question of physics in the universe. That's the fundamental question. How do things work? How does gravity work? Over what scales? Things of this sort.
Gravity dominates on the largest scales. The planets, stars, and galaxies all are ruled by gravity. But gravity also affects the tiny particles that form light. Gravity from a large object will bend light, distorting the background image. Astronomers call these curved images gravitational arcs. Light will be bent by any dark matter contained in the foreground. Tyson is searching for these gravitational clues. Gravitational arcs can arise from any type of matter, luminous or dark. Chile, the town of La Serena. The nearby observatories make La Serena a natural stopping-off point for astronomers. Beyond the town, the land is sparsely settled by peasant farmers. In the foothills of the Andes lies one of the world's major observatories, Cerro Tololo. Observatories are worlds unto themselves, outposts in our quest to know the universe. Astronomers usually come for 2 to 5 nights on an observing run. The routine is much the same at observatories around the world. Sleep during the day, eat in the afternoon, and work all night. Tyson has come to Cerro Tololo for a 2-night run. Assisting him is Raja Guhathakurta from the Institute of Advanced Study in Princeton.
Okay, let's see. We've got 3 of these.
Tyson's search for gravitational arcs begins by finding places in the sky that appear empty.
See anything interesting? Places where there aren't things like that. It seems a little strange for astronomers to to look at places in the sky where there's nothing, but in fact, what we found was that there were just lots and lots of galaxies in these rather tiny fields where there just happened to be nothing on these photographic plates. We found 1,000, typically 1,000 faint blue galaxies.
Galaxies are the building blocks of the universe. Usually they occur in clusters containing thousands of galaxies. Probing the darkness beyond the clusters, Tyson discovered that the space was not empty at all. There he found numerous faint blue galaxies. These galaxies provide a luminous backdrop, a curtain of light that Tyson can use to search for gravitational arcs. The light from the background galaxies will be bent by any dark matter contained in the foreground. This creates gravitational arcs, the fingerprints of dark matter.
Knowing that the sky is peppered with this backdrop of roughly 20 billion faint galaxies, we can use those faint galaxies as a tool to study the foreground dark matter.
Oh,
That's certainly a candidate, isn't it?
Yeah, as is that one there.
Astronomers make the short trip to the telescopes in a Volkswagen. Once they used golf carts, but when funding became available, the observatory upgraded. All the cars are of the same vintage, with the same mileage, and they rarely get above second gear.
When I was a kid, starting out in science, it was difficult in the local libraries to find any books on science. I found a little tiny thing once on linear accelerators, sort of a popularization of linear accelerators. And so I built one. The thing practically exploded. I think there were a couple of people that affected my vision of what I could do in science. And that was in the 6th grade. I had a teacher who encouraged science experiments. And then later on in high school, there was a science teacher that encouraged experiment and observe. Individuals make a difference.
We should go in and focus very soon.
Well, Raja was a very good student, and he's I think, going to go quite far. He brings to the project a great deal of enthusiasm and also a very broad understanding of the astrophysics behind it.
Tonight, Tyson will use the largest telescope on the mountain, a reflector whose mirror spans more than 8 feet. Outfitted with the latest electronics, this telescope is one of the most powerful in the world. The control room of a large telescope resembles a flight deck, crewed by a pilot, a navigator, and a man at the helm.
I can move it down if you want. Thank you.
Astronomers seldom get more than a few nights of telescope use in a year, so observing runs are well planned.
Every second counts. This is a big telescope, and we get very little time on big telescopes. It's very highly competitive, and we have lots and lots of observing to do.
Tonight, Tyson will aim the telescope at several targets.
Okay.
Charts and star maps are used to navigate.
Yeah, I'll do that in a second. Okay. This gives us a nice finding chart. It helps us find our way on the sky, if you like. I mean, by looking at the stars there and comparing it with what we're seeing now, we can tell whether we're in the right part of the sky or not.
To search for gravitational arcs, Tyson must meet two objectives. Image the background galaxies, then find a foreground cluster. If the cluster contains dark matter, Tyson should see gravitational arcs.
That's just about right. Okay. Thanks.
To succeed, Tyson must look deep into space, pushing the telescope to its limits. A telescope is a time machine. Tyson looks back to a time over 12 billion years ago when the first galaxies were forming and the universe was emerging from darkness. Tyson's first stop is a seemingly empty region of space. The background galaxies are much fainter than the natural glow of the night sky. To distinguish galaxies from electronic noise in his detectors, Tyson jiggles the telescope. Eventually, the faint blue background galaxies appear. Now Tyson must find a foreground cluster. If the cluster contains enough dark matter, the light from the background galaxies will form gravitational arcs. Though dark matter is invisible, Tyson believes his technique allows him to create pictures showing its shape and distribution.
The most significant thing about what we're doing currently is that this is the first time that we've been able to actually see dark matter. We can actually image the stuff and get a picture of it. And these pictures, the way it appears on the picture, if it's clumped or stringy or just a nice little round blob, I think is going to end up telling us something about its nature and about the history of the universe and the way things eventually clump together under their mutual gravitational attraction.
My feeling is it could be these three.
Tyson records his images on computer tape. Only after careful analysis can he be certain he has detected dark matter.
Well, I thought I convinced myself a few minutes ago that I could see some more blue arcs in this thing, but we'll have to wait for the data reduction. Okay. Can you guide on that?
Through the night, they'll continue to work, aiming the telescope, capturing light that began its journey 12 billion years ago. A few weeks later, near Princeton, New Jersey, Raja Guhathakurta is on his way to Tyson's laboratory. There, they will analyze the data they gathered in Chile.
Tony is great fun to work with. It's always
excited about the projects he's doing, and he does generate a lot of excitement, and he does do interesting science.
Bell Laboratories at Murray Hill is one of the few commercial institutions to employ astronomers.
The computer setup there is ideally suited to this kind of reduction procedure, so it's most convenient to try to transport ourselves there instead of trying to transport all the software and equipment to another place. What we'll be doing is essentially reducing some of the data that we collected on this last observing run in Chile.
This should be returned to the tape archives. This is the final production image in color. These fuzzy yellow things and fuzzy red things, those are the galaxies that are in the cluster in the foreground. And see all these blue guys? Those are all distant galaxies, way, way behind the cluster, many times further behind the cluster. And there are visible by eye many examples in these blue galaxies where they're aligned along circles centered on the center of the cluster. So these galaxies have been stretched. Their images have been stretched by the gravitational lens effect of the cluster. All the mass in the cluster causes these galaxies to appear at a different place on the sky than they would have otherwise. And as a result, their images have also been distorted systematically into these segments of circles around the center. And what Raja and I are going to do now is to start up some software which will analyze this final production image. It will create a picture of the dark matter in the cluster.
Using a computer, Tyson creates a simulation of the gravitational effect of dark matter.
What we do is we simulate the universe and then compare the results with what we find through the telescope. And it'll tell us if the simulation is wrong or right. And when we get a good match, then we move around in parameter space to see how robust that match is. And that tells us quite a lot about what's really out there.
Using this technique, Tyson estimates that 90% of the universe is in some unknown and invisible form. Dark matter lies not just in the distant universe that Tyson explores, it permeates the universe around us. All that we see is only the tip of a greater universe submerged in darkness. Dobson's stay at Crater Lake is over. It's time to move on. He carries his observatory in the back of his van.
The reason I got into this telescope-making world is because I wanted to help make it possible for people to see this world. And that's why we made these user-friendly telescopes. They're not designed to entertain photographic plates. They're for entertaining soft, warm eyes. Because seeing things in photographs is a very different thing from seeing them with your eyes through a telescope.
Every summer, Dobson travels to parks and small towns. He stops wherever people gather, giving his talks and holding his star parties, preaching the joys of astronomy.
You see at all these places you go, there are so many people who are terribly interested in these things. And then you have to understand that the population of this earth is several billion, and all those eyes are waiting to see, all those ears are waiting to hear, all those minds are eager to understand. And somebody's got this job to do.
In the span of Dobson's life, astronomy has dramatically changed our view of the universe. Not long ago, we knew of only one galaxy, our own, the Milky Way.
See, when I was a kid, the universe didn't look like this at all. We only knew that we had one galaxy, our own galaxy. Nobody talked about galaxies in those days. They were called spiral nebula, the Great Spiral Nebula, and Andromeda, all that kind of stuff. All that's changed, and when Einstein came up with his gravitational theory, that's really when cosmology got going. And also because at the time we found out that there are galaxies outside of our own, and we wondered how far it goes. And so really the scientists took this broad view in the early part of this century, and that's running wild now.
At home in San Francisco, Dobson gives classes in telescope making at a nearby museum.
The class at the Academy of Sciences, they have a big enough mailing list so that they can get enough people together to run a class. And the class runs for 8 weeks.
Dobson is well known among amateur astronomers. The Dobsonian telescope design is world famous. The instruments are hardly high-tech, but they're easy to build and a joy to use.
Rough grinding is a caveman's job. That's what we do this week. Rough grinding is a caveman's job. Eat well, sleep well, and work like hell. But there's nothing about it that we don't know how to do, and there's no boo-boo that you can do in this class which will be followed by a life of sorrow. The worst state you can possibly end up in is not having a telescope, and that's where you are now. I want them to see the universe. As I said before, I want them to see the universe, because if they don't see what the universe looks like, they won't wonder about it. And if they don't wonder about it, they're dead. What's the use of somebody that doesn't wonder? It's the hallmark of our species that we're continually wondering what's going on. But the specialty of these things is that they move easily. They go wherever you push them, and they stay wherever you leave them. But they don't track things across the sky. They're not good for photography, no. If you want to do photography, well, in the first place, you've got a disease, because all the pictures have been taken by Lick Observatory, and all you have to do is go and buy them. You can't buy film for the price you can get the pictures. But nowadays, what they do is to make this kind of a mount anyway, even if they do want to do photography, and then they put this on a Ponce mount. Now, Ponce is a Frenchman, and he writes to me, and he apologizes from France, and he apologizes for redesigning the Dobsonian. Anyway, he thinks that's real funny. And what we're going to do is to... When I joined the monastery, I was working in the atom bomb project, the Second World War. I was working for the University of California, the radiation lab. And in the monastery, I became keenly tied up in these cosmological problems, if you like to think. So I wanted to see what the universe looked like, and so I helped somebody make a telescope, and then through that telescope, we saw the third quarter moon. And as soon as I saw that third quarter moon, it looked as if they were coming in for a landing. I couldn't believe that the moon would look like that. And I thought, my God, I mean, inside of me it said, hey, my God, everybody's got to see this. Oh, now here's a polished one. These people start with a raw hunk of glass. And then even with the unsilvered mirror, they look at the moon and they can see all those craters. They're flabbergasted. That's what gets everybody. I'm not interested in telescopes. I really am not. And if I had to just sit around making telescopes for sale, I'd be long gone. I really am not interested at all. Now, you see all these people, the reason they're connected with me is because I stand for something, for some information about this universe. They're not interested in me. They're interested in the information, and they've never seen this information put in a package before. That's the fact. In there. All right. Keep going. Nothing's happening.
I'm turning it.
Alicia, your mirror is too deep in the hands and a little bit flat in the fingers. Somebody sticks around when he feels that he's got something to do. You know, old people that don't feel that they have anything to do and they feel that their friends don't love them anymore, they die fast, okay? People who feel that they have something to do and they've got friends whom they care about, they don't die out like that. I'm one of those guys.
Watch TV, you could get your head knocked out.
Get you out quickly. Well, the song is an old thing. It's Shankara's, and Shankar is something like 800 AD or something like that. And his view is that behind this whole universe there's just one reality.
I'll do it here.
Om Vishwam Darpana Drishyamananagari Tulyam Nijantar Gatam Vaishyanatmani Maya Bahiriboda Bhutam Yata Nidraya Yah Sakshi Kurute Prabodha Samaye Svatmanameva Vyayam Tasmai Shri Guru Murtaye
On the big island of Hawaii is a dormant volcano, sacred to the Hawaiians. At an elevation of nearly 14,000 feet, the observatory on Mauna Kea is the highest in the world. At this elevation, minds grow fuzzy, muscles ache, and breath is short. But astronomers dream of observing at Mauna Kea, for here is where the answers to today's celestial mysteries may be found. To continue his work on dark matter, Tony Tyson has been granted another observing run.
This kind of research isn't very glamorous. It's a lot of hard work. The observing can go well sometimes not. It's long hours, and the successes are occasional, but when they happen, it's fun. There'll be generations of researchers after me who will still be researching the dark matter problem. Basically, all we're trying to do is to provide some limits to how it clusters and where it is so that people can try to understand what it is. Okay, well, being optimistic, I'll put the tape on anyway. There is an aspect of being close to nature, of being alone with nature, in fact, that science has, not just astronomy, but any kind of scientific research.
The fundamental question that astronomers would like to answer is, what is dark matter? What is this stuff that does not shine? Planets do not emit light as stars do, so planets are a form of dark matter. But astronomers doubt that there could be enough planet-like objects to account for the amount of dark matter they believe exists. Day begins to contract.
Well, I think life on Earth has a lot to do with the universe as a whole. I think our perception of ourselves is somehow shaped by the way we view the universe around us. But it's difficult to go through life realizing that over 90% of everything in the universe is something you know nothing about, and it may be made out of particles that are zipping through your body even now. I think it's certainly worthwhile trying to answer that question, build machines that will try to answer that question. Unless you take the risk and build the equipment and design the experiment and ask the question, you don't ever get any closer to the answer, and you don't ever get any closer to nature. It's totally up to the programmer.
We have to write something like that, because he writes something like that yesterday, but I don't know what.
Astronomy has become big-budget science. Access to major telescopes is competitive. Sometimes it takes great ingenuity to conduct unusual experiments.
You get some crazy idea in your head, right, that you can't get rid of, and you want to test it. So you design an experiment to test the idea, and then you try to carry it out in the laboratory or in physics or in astronomy with a telescope, perhaps.
No,
We did a bizarre experiment in '84 by pointing the telescope at a place where there was nothing on the sky. It was done secretly because there's no way that you could get a committee of astronomers to agree that this is top priority. But when we started finding things, it got real interesting.
Tyson's chance discovery, the faint blue galaxies, became a new tool in the search for dark matter. This is the way of science. New discoveries lead not only to answers, but also to new questions.
The idea that dark matter is around us has been around since the middle 30s. It was simultaneously discovered that, on the one hand, there was something in our galaxy pulling stars back stronger than the gravitational pull of the known stars. And roughly the same time, galaxies in clusters of galaxies were found to be rushing around faster than the local speed limit, which is set by the gravitational pull of all of the galaxies that one can see. So there was something there, some extra mass. We're turning back now. The guide camera's ready. Are you guiding?
That 90% of the universe has some invisible and unknown form is an accepted astronomical fact. The puzzle of what it is now ranks as one of the great mysteries of the cosmos.
Also towards the hunting dogs, we find the stars and galaxies and scribble in our nightly logs. Some major, minor, Vela, Virgo, Volans, and Vulpecula is where we plan to aim tonight with $1,000,000 specula.
Kevin Krashunas is an astronomer who works year-round at Mauna Kea.
In hot pursuit of photons there and world-beating science. Songs like this I have actually had to write. Well, let's say I did write them in preparation to go give talks at astronomy conferences. There are a number of important considerations in choosing a site to place a $10 or $100 million telescope. You want to be clear often, which it is at Mauna Kea. You want it to be dry so that you can do infrared astronomy. And you want to be within 50 miles or so of the ocean, because they found that you get a smooth flow of air over the top of the mountain, and this leads to very steady images.
The clear air of Mauna Kea attracts astronomers from all over the world. Half a dozen countries have built telescopes here, and more are planned.
We are through Millimeter Wave Valley, and we are heading up towards the mighty Keck, which will be 4 times the power of the Palomar Observatory telescope and will, by a long shot, be the world's largest optical and infrared telescope.
The size and innovative design of the Keck telescope will provide better views of the universe than ever before possible.
There are 2 unusual things about how the telescope is designed and will be built. One is the mounting, in that it's an alt-azimuth mounting similar to a Dobsonian mounting because you can build it cheaper for any given size telescope. This one, of course, has to be computer-driven. The other unusual thing is that it will have a mosaic mirror. Rather than a single piece of glass, this will have 36 hexagonal mirrors, 1.8 meters in size.
Astronomers use the term first light when a new telescope first captures starlight. The Keck telescope saw first light in the fall of 1990.
At the other end of the Keck dome, it is within the realm of possibility that they'll put another telescope just like it so that you can combine the signals of both telescopes as if you had 10-meter binoculars. This is beyond the technology at the moment, but in 10 years or so, who knows? At last, here we arrive at the summit of Puupoliahu. We're at the summit of Puupoliahu, the second highest cinder cone. But as you can see before us, there's this beautiful panorama along the summit ridge and in the valley in between of the jewels on the mountain. When I was a kid, I thought, well, maybe if I'm lucky, I'll get to grow up and play with things that I couldn't afford myself. And so I feel like I've done my fairy godmother a turn in reverse by studying hard enough to get a decent enough job to work with this kind of equipment with the other people that come up here. For those occasional nights where something really, really exciting rolls off the telescope, it's great to be here at the forefront of technology and science.
Vera Rubin remains intrigued by the problem of dark matter. For now, she's involved in other projects, moving forward to new problems and challenges.
I brought some things I got at Kitt Peak. After Andy and I were at Palomar, I went off to Kitt Peak and I took some spectra of not normal field galaxies. And they really there are enormous ways to get pleasure in doing science. I've just come back from 3 spectacular nights and see things on my spectra that I've never seen before. This is a very exciting time. So every day is really very exciting. I don't know what will come out of this. I don't know whether it will be major or minor, but it is an enormous pleasure to see things you've never seen before and to attempt to understand them.
In downtown Washington, every Saturday, the Carnegie Institution opens its doors to the children of the neighborhood. The program is called First Light.
One of the planets that are going around it. And this is a model of all of the planets around our sun. But it's really very, very, very many times smaller. Yes? We all recognize the really severe need to interest youngsters in science. That, you know, in the year 2010, these are the kids that'll be doing science. No, it's over here.
Rubin is one of several scientists who help the children of First Light discover the joy of science.
Okay.
Dobson's students have completed their telescopes. Now he takes them on a star party. These telescopes, too, are ready to capture first light. Whether their telescopes are small or large, all who look to the skies and wonder are astronomers. They delight not only in seeing, but in the endless struggle to understand.
What we're doing really is an experiment in experimental physics. There's a mystery. The mystery is the mystery of dark matter. I don't think that that's leading us to any great new philosophical or theological worldview or universe view. It's solving an interesting problem, and it's exciting and fun.
And if you're looking at that side, you'll see that one side is light and one side is dark. Yeah. This side is it's been almost 10 years that we've talked about this dark matter, maybe even more, for real. And I thought 10 years would give us the answer, and it hasn't. And I think that means it's a tougher question than we thought. And I think it may be full of surprises when it comes out.
Everybody's tied into what he feels to be real, okay? And when he looks out with the telescope into that vast, almost empty darkness, he knows that is real. Everybody gets that feeling. And some people get swept away by it, really swept away by it. Their life gets completely changed just by looking through these telescopes, really.
We're all crowned our own mirrors, I suppose you know that.
Stay tuned for more scientific adventure on The Shape of the World, coming up next on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Video cassettes of the Astronomers and a complete set of educational materials are available from PBS Video. To order, call 1-800-222-5796 or write to the address on the screen.
This is PBS.
It only happens once a year.
Cary Grant and Katharine Hepburn are bringing up baby. Plus,
ever since I've met you, I've swept you off my feet.
You play blackjack, soccer.
It's the Marx Brothers in Animal Crackers. 3 favorite comedies, Saturdays starting at 8 p.m. on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Once, the universe was viewed as serene and unchanging. But today we know of great cosmic forces, power beyond description. Astronomers believe this power comes from the dark force of giant black holes. Galaxy NGC 1275, a galaxy that could solve the mystery of the most powerful objects in the universe. Jesse Greenstein, co-discoverer of quasars. Tony Reedhead, searching for the source of their power. And John Conway, chosen to lead an international effort using a telescope half the size of the Earth.
I mean, you can't produce an image of NGC 1275 just with one telescope. We have to use telescopes in different continents. So we've got telescopes in Bonn for this experiment, in Germany. We've got Richard Porcus, who's collaborating with us, and he's working there. And then Tiziana Venturi, she's a telescope in Sicily.
Next, on The Astronomers, searching for black holes in the heart of a galaxy.
Tim, do those helium spectra look okay?
As the day ends, another journey of discovery begins.
We want to look at some active galactic nuclei and quasars tonight, and we're going to start off with observations of NGC 1275. Can you put the coordinates in? And I'll go.
Tony Reedhead investigates the most powerful galaxies in the universe. Reedhead will use the 200-inch telescope on Palomar Mountain, one of the world's largest. Tonight he will probe deep into space, exploring the hearts of galaxies.
Science is certainly an adventure. It's a continual voyage of discovery. It seems to me remarkable that we can do experiments here on Earth and then translate this experience to what's going on in a distant star or a distant planet or in a distant galaxy.
The adventure of astronomy unfolds in majestic mystery. Once we thought a galaxy was merely an oasis of billions of stars, floating in quiet serenity. Some have distorted shapes, others ghostly tentacles. Strangest of all are the distant objects that appear as only faint points of light. Quasars look like stars, but are really the centers of the most distant and powerful galaxies. A quasar can outshine 1,000 normal galaxies. To seek the source of this enormous power, astronomers use a different way of seeing. The glare of the visible world conceals the radio universe. A universe detected by radio telescopes, like these at the Very Large Array in New Mexico. The VLA is the most complex radio telescope in the world. Each of these 27 dishes is connected by computer to form a single telescope 20 miles across. The VLA provides a view of the cosmos 5 times more detailed than the optical telescope at Palomar, and it provides a different kind of picture. When the dishes are aimed at a galaxy, detected radio waves form a map, revealing unseen regions shining with radio energy. The location and intensity of the radio waves are coded with colors. Through radio telescopes, astronomers have discovered that some galaxies radiate far more energy as radio waves than as light. One such galaxy astronomers call NGC 1275. 1275 is not a quasar, but it bears a family resemblance. Like a quasar, the galaxy produces most of its energy in a tiny region at its core.
An arc minute is 10 kiloparsecs, but that's sort of 60 arc minutes.
Tony Reedhead of Caltech is a leader in the study of
I'm
quasars.
trying to think of the whole scale here. But of course we want to go in a lot deeper to the core of NGC 1275 here.
Reedhead views 1275 as a mini quasar.
It would take 10 million years to produce that total
He
energy.
believes the galaxy's energy arises from the same process that powers quasars.
Well, here you're looking at a region in NGC 1275, and the interesting thing is that it has this very bright and compact active region, which is very bright in the radio. Now, if you looked at this object optically, it doesn't seem all that extraordinary. It's a slightly unusual galaxy, but not very unusual. But it turns out that a very small fraction of galaxies, which look quite ordinary in the optical, when you look at them in the radio, have extraordinarily high radio emission. They're very energetic objects. So the energy that's pouring out of here in the radio is more than the sum total of all the energy that's coming out from the whole galaxy, all the stars in the optical.
Only one thing seems capable of generating so much energy in so small a space: a giant black hole. Enormous black holes may lurk in the hearts of galaxies. Galaxies were born from great clouds of hydrogen gas, brought together by the hand of gravity. At the very center of the cloud, the gas is squeezed ever more dense. If dense enough, a black hole will form. Feeding on the surrounding gas and stars, the black hole can grow to the size of our solar system, and nothing can escape from it, not even light. The gravity of a supermassive black hole could be the engine that powers quasars. But how does the engine work? How can gravity be the source of such enormous energy? The force of gravity wasn't always so mysterious. Visible light was once the only way to see. But then astronomers found a new window, the universe of radio. Jesse Greenstein was a pioneer in the discovery of quasars. He was an astronomer before black holes were even equations on a chalkboard. It was a different universe, a different time.
I had been interested in astronomy, and I wanted to go on in science. And I got a master's degree at Harvard in 1930, and then all hell had broken loose. I saw people jump out of windows. This was the great bottom, the Depression. My father and grandfather and uncles and so forth beat on me that I ought to be in the family business, that fresh blood would bring back the family fortune. So I tried it for 4 years, and it was a lot of fun in the sense that I hated it. By 1934, I asked my present wife to marry me, and she said yes, but not if I stayed in business. So I gave that up and became a mere fact finder, and I've enjoyed it ever since.
The search for facts led Greenstein to Pasadena, California. Caltech's Palomar telescope had just been built. Optical astronomers were having a heyday, but radio astronomers had barely begun. With only primitive telescopes, they could not identify the sources of the unusual radio waves they were detecting. Their radio pictures lacked detail. Help came in the early 50s from two optical astronomers working at Palomar, Walter Baade and Rudolf Minkowski.
They fastened on these two great observers at Mount Wilson and Palomar, Walter Baade and Rudolf Minkowski. Great men, completely open to suggestions, with very little theoretical interest, but amazed at the beauties of what they could see in the universe and really turned on by the excitement of things radio astronomers saw that were not obvious.
Using the new Palomar telescope, Baade and Minkowski searched for clues. They discovered that the unusual radio waves often came from peculiar-looking galaxies. One such galaxy was NGC 1275. In their pioneering work, Baade and Minkowski paved the way for younger astronomers like Greenstein.
Baade kept chow dogs of unbelievable ferocity, which would devour strangers. Anybody who laughed loud was liable to lose an arm. Minkowski could not ever stop talking in a conversation, and he filled pauses by a rumble sort of, and so Minkowski was not dreadfully well organized. On the other hand, he had a kind of genius, so that if you asked him, what about that letter? He'd say, and he would look at this 2-foot-high pile of scattered papers, and he would lift up the pile and pull out about an inch of papers, open it, and there was the letter. Or there was a plate, and he would reach for the bloody plate, and he would get a magnifier and hold it up against the light box and say, see, and I'd say, where? And he'd say, see, and he had a thumb about 1.5 inches across. He'd put his thumb on it, and I'd say, great, don't touch it. It's all right, Jessica, all right.
Optical astronomers and radio astronomers continued to work hand in hand. Powerful radio sources were pegged to galaxies visible through optical telescopes. For Greenstein and his colleagues, the identification of these intense radio sources became almost routine. Then in 1964, the world of astronomy was rocked by a single discovery. Martin Schmidt and Greenstein had been investigating mysterious radio stars they called quasars. One night, Schmidt discovered what he at first thought was impossible. These quasars weren't stars at all, but the most powerful objects ever seen, shining more brightly than most galaxies.
In the paper that Martin Schmidt and I wrote in 1964, we have in several places the remark, this is much more energy than we can account for. And we don't know where it's from. We imagine, in fact, that there is at the heart of this quasar an object we call X, which is doing it. Object X. And that's the end of it, because we have no explanation.
Today, astronomers believe Object X to be a supermassive black hole. Quasars and black holes are hot topics at astronomical meetings. This one brought astronomers from around the world, including Tony Reedhead from California. Also Arno Witzel from Germany.
Those timescales of weeks or so, where he found his 1 or 2% variability in compact, mainly in compact sources.
Papers were presented, views exchanged.
And I'll show you briefly here.
The meeting was judged a success, but as with most meetings, the real progress came later. At a nearby restaurant, Reedhead gathers a group of radio astronomers who all have a deep interest in quasar-like galaxies such as NGC 1275.
1275 is an elliptical galaxy, which is about 70,000 light years across. When we look in the center of this object with, for example, the Very Large Array, the VLA, we see that there is a very interesting structure, which I'll have to expand here for you. And if I draw out that structure, what we find is that there's a very, very bright core. Now, of course, what we're really interested in is what is the beast in the center that can do this, because it's an enormous luminosity that we're talking about here. It's about 100 billion times the luminosity of the sun. So it's an very high luminosity, and it's coming from a tiny region. Now, the idea is that these are actually fueled by supermassive spinning black holes.
They decide to launch a major investigation of the galaxy.
Which is quite a long way in front, in fact.
The group includes Tiziana Venturi, an astronomer from Italy, and Richard Porcus, working in Germany. John Conway, a postdoctoral fellow at Caltech, has convinced Reedhead that he is ready to lead a major investigation. Now he'll get his chance. The observing team will link radio telescopes in different countries, creating the effect of a single dish thousands of miles across.
So if you want to think of it graphically, you start out with Onslow, okay, and then you go a bit further south, and then there's a 100-meter telescope in Bonn, Okay, and then a bit further south than that, there's the 32-meter telescope in Noto in Sicily. Okay, and then those are the 3 telescopes that we had in Europe. And then you come across the country, and there's a telescope in Haystack, which is Massachusetts, and the VLA, and 2 new telescopes of the VLBA near the VLA at Pie Town and at Kitt Peak, and then the Owens Valley radio telescope. The Owens Valley radio telescope. The Owens Valley radio telescope, right? This was the center of the nerve center.
If the team is successful, they will create an instrument thousands of times more powerful than the 200-inch Palomar telescope. The linkage of radio telescopes is called Very Long Baseline Interferometry, or VLBI. As the Earth turns, the telescopes in Europe will be the first to detect the galaxy. The network of telescopes will span 6,000 miles, forming a system that sees as clearly as a dish almost as large as the Earth.
KIBS here in beautiful Bishop, California. It's about 25 now past 6 on a beautiful High Sierra day, and again, big time 6.
Goes wrong during the observations, they can get in touch with me. I'm the central person to coordinate things. And that's basically what the PI does. And usually the PI also does most of the analysis afterwards.
Conway has come to the observatory located in Owens Valley, California. It is one day before the observation of NGC 1275 is due to begin.
For a young astronomer like me, it's very difficult because there are only a few permanent jobs in the subject. I mean, you work for 2 or 3 years in one place, and then generally you have to move somewhere else. For a long time, I wanted to be an astronomer, and you start thinking about going out and getting a real job sometimes. But then I don't know really. It's not something, just looking at the universe.
Conway has a lot riding on this experiment, but he's not going to play it safe. He's going to try something different. In his PhD work in England, Conway proposed a new method to make VLBI even more powerful. This experiment will give him the chance to prove his idea works. The technique requires changing the detectors at each site so that they can observe at more frequencies than normal. The extra work doesn't bother Conway. It's the weather he fears. If it rains on any of the telescopes, the data could be washed out.
The problem is that particular frequency, that affects you as water vapor in the atmosphere, which can reduce the sensitivity and cause problems. If the weather's bad at a lot of the sites, then it really affects the experiment.
To Conway, this observation has become more than a test of his concept. It's become a test of himself, a rite of passage.
point about is this accumulation of knowledge, that everybody makes their own observations, and eventually it becomes part of the total knowledge. When you look back over a long enough timescale, you say, well, what have we come in the last 10 years? And you find that we've actually discovered quite a lot about these objects, and we've actually made a lot of new discoveries. We know that everything's going to get better, you know? We know that when we do this experiment a year from now, we're going to have more telescopes, we're going to refine our techniques, we know that the data is going to be better, we know we're going to get better images. So I'm optimistic that we supposed to be in 10 years' time, we will have made just as much progress as made in the last 10 years.
The coast of Sicily. Tiziana Venturi is traveling to the radio telescope near the town of Noto.
You always have the opportunity of getting to travel a lot. This is something which is really, I really like. I'm really enthusiastic about that.
Venturi is an Italian from Bologna, now working at Caltech. On her first trip to Sicily, she passes through the ancient city of Siracusa. For most VLBI observations, technicians can operate the telescopes unaided. But Conway wants nothing to go wrong. Venturi has agreed to supervise directly.
We are waiting for the run to start. So at that point, our observation will start, and then it will carry on like for, I think, 18 hours or something like that. So now it's just very, very tedious stuff. You don't really have to do anything except writing down like the system temperature, the antenna temperature, and you have to stay up hours and hours and changing the tape every 4 hours and keep on checking. It's really boring. In radio astronomy, you have to wait for months. In VLBI, it's even worse because then, since all these radio telescopes are independent, then you have to correlate your signal, and this requires time, and then you have to reduce stuff. And it sometimes takes you like 6 or 7 months before you get an image and before you realize whether all your efforts were worth.
Bonn, Germany, the birthplace of Beethoven. Overseeing the German link in the experiment to observe Galaxy 1275 is Arno Witzel of the Max Planck Institute.
If you look at the optical picture of NGC 1275, it is sort of chaotic, but it is beautiful, there's no doubt. That's another meaning which it has to me. And then it is kind of a challenge. We still don't know what the physical processes finally are, which make such energies. We have ideas about it, and I'm sure you will hear a lot about that, but we don't finally know it yet. And so it is a challenge, and I think it will be for some years. Mankind lives for 100 years, if we are very optimistic. But cosmical processes normally take place in millions and billions of years. If we look to several points, to very many points actually, we see galaxies at all stages of their life. When they are being born, when they evolve, finally when they die. It takes me only something like half an hour drive to go from the institute, the Max Planck Institute, which runs the telescope, to the site here in Effelsberg. So we have both. We have the telescope nearby, close by, and we have a beautiful surrounding whenever we go out there. So over there we have our nice little toy, the world's biggest steerable radio telescope. It was built in the late 60s, actually between 69 and 71, at incredibly low cost, one should say nowadays. It was about 30 million Deutschmarks at the time being, which is nothing for such a beast, I think. And it has an enormous collecting area. The area over there of the surface is bigger than the area of a soccer or a football field for the Americans. We are setting up an experiment on the Seyfert galaxy NGC 1275, and the astronomer who leads that experiment here in Bonn is Dr. Richard Porkes, whom you see over there in his green shirt.
We know clearly that in the case of quasars, just to get the energy out, there must be a very, very compact and massive object at the center. It may be a black hole, it may not be a black hole, we don't know, but it must be very massive. And also in the case of NGC 1275, that's clearly the case also. We see signs of the same sort of activity as in quasars, especially in the radio. And exactly what the relationship between these different classes of galaxies is, I can't tell you.
The instruments have been fine-tuned, the telescopes aimed, the computers are all in readiness. Now, before the investigation can begin, the astronomers must wait. Wait for a galaxy 200 million light years away to rise into view.
2.65. 10. Yep. Radiometer. Those meters are in scale, yeah.
Poi questa è la schedula che ha mandato John Conway.
The galaxy 1275 has been detected in Europe. There, telescopes have picked it up and are tracking.
In Europe, it's now well overhead, but here it's just groveling around the horizon. Yeah. So it's very close now. Yes, and in fact, yeah, okay, great, we're tracking now, so you actually pick up the source. It's just come over the horizon, and great. the program started.
VLBI observations are not like looking through an optical telescope. All the telescope signals must be combined later. Only then will they know if the experiment has worked. They must observe blindly. So some take life easy, while others keep checking and double-checking.
40, 50, 60, 70, 80. 0, 10, 20, 30. Looking at things like NGC 1275, you've got to have some sort of picture of what's actually happening, otherwise you can't make sense of anything. So it's a key to actually imagine being there. And if you can imagine being there, then you can hopefully get more science out.
No human could survive a journey into the core of a galaxy. But we can imagine what it would be like. Near the core, stars crowd together, and the gas between them grows denser. The temperature rises to heat a surrounding cloud of gas. Beyond this veil lies the supermassive black hole. Around the black hole spins a vortex of gas and stars swirling towards oblivion. No radiation can escape from the black hole. Astronomers would see only the spinning disk around it. Stars and gas orbiting close to the center risk being drawn into the black hole. Stars trapped nearby are doomed. Material is shot outward in a great jet of high-energy particles. To astronomers, these jets are beacons pointing to the black hole heart of the galaxy. – 3 o'clock in the morning, 6 hours into the observation. Conway discovers that a piece of equipment has been malfunctioning. Now he wonders if he's been observing anything at all.
Disconnected the 5-meter telescope network.
Yeah, they thought that was what was causing the crash.
I still think it. Special ports like the one used to control the 40-meter have to be configured in a special way.
I think 367 is still up. I'll try it. Oh, okay. Seems to work. Basically, it was just a piece of equipment hadn't been connected properly. So that means most of the calibration information up to now has not good. But I don't think it's actually affected the data we've got, so that's the main thing. It's like, it's bad, but it's not a disaster. We've got the data, I think. So that's the main thing. And hopefully it should be a boring night from now on.
We just don't know yet, of course. There's always this problem when you observe that, especially with VLBI, you're never quite sure that you're doing it right. You're sitting here, sometimes doing nothing and just hoping that the thing is working.
The antenna is working perfectly, and all the numbers are sort of what we expect. That's pretty good, yeah.
I dabbled in amateur astronomy and stuff. I remember at school I was a member of the Astronomy Society and stuff. But the problem was that I like the idea of amateur astronomy, but it was just too cold, you know. And but then I got interested again when I got interested in the physics of what was going on. So see, I come back to it, and it's not quite as cold when you're doing it professionally.
Well, I don't really feel fortunate because I'm an astronomer. I just feel fortunate because I'm doing what I wanted to do. Astronomy and physics and all these other scientific disciplines and subjects are important in the same way like paintings and philosophy and literature. what I feel is that, I mean, even if in sort of small amounts, but I'm contributing to this, or also all the astronomers really are contributing to this overall knowledge. And this is what astronomers do and what other people in any other discipline do.
There are always people who want to do an experiment which shows a theory wrong, and I think I would class myself more in that line than those who are trying to confirm a theory. But it's merely a question of outlook. I mean, it doesn't affect what the result of the experiment is, of course. Maybe affects what experiments you choose to do.
Ah, ho capito. E che numero dovrebbe? Cioè, io non le so proprio queste cose. Un orrore. Io, cioè, appena vedevo un numerino, una notte ho svegliato.
This experiment may test a favored theory that black holes are fueled by other galaxies.
One of the reasons why it is thought that, I mean, galaxies in the center of clusters of galaxies are bigger and more massive simply because they create material by interaction with other galaxies, and therefore, I mean, they just collect more material, more gas and everything, and that they just get bigger and bigger. And that's the case for NGC 1275 too, since it's at the center of this rich cluster of galaxies.
Galaxies are rarely born alone. Usually they come in clusters. Sometimes they interact. A larger galaxy may cannibalize a smaller one, gaining new material to feed its black hole. The black hole attracts the gas and stars of the smaller galaxy. The infalling material joins the rotating disk, heating it still further. The material that feeds the jets is ejected at nearly the speed of light. The black hole and its disk have become the most powerful cosmic engine in the universe.
Sarò lì. Saranno pane quotidiano. Dio, che orrore, non farmici pensare, guarda. Una piccola schifezzina. Però noi le uniche informazioni.
So far, the observation has gone well. But now, with 4 more hours to go, a slow-moving storm is spreading rain over northern Europe, affecting the telescopes in Germany and Sweden.
This is when we did a check to make sure we were on NGC 1275. We do a cross-scan procedure whereby we just drive across the source and we hope that the source peaks up in the middle. Well, it more or less does here. This is the characteristic response you get when you drive across the source. And further back, you'll see here that the output level went off scale because there was rain.
Okay, I just thought I'd mention that, just to be sure. Okay. Okay, well, if you can't... Okay, thanks anyway. Bye. Okay, the weather wasn't very good then. And didn't have time to make some of the calibration measurements they would like, but that's okay. That was Sweden, yeah. Yeah.
This experiment is a rare opportunity. It offers the best chance to explore the power source of 1275. Astronomers believe it may also help explain the far more distant and powerful quasars.
Quasars are very interesting objects since, on the one hand, they are the most distant object in the universe we know, which also means that they were produced very long time ago. And the very fact that we see them here on Earth means that they have to be enormously powerful. And in fact, they are the most powerful objects in the whole universe we know of. This is VLBI observations of quasars. Look at these marvelous jets here. You see we have regions here shown in different colors of different temperature, of different energy. This proves that we have a source of very intense radiation, and from theoretical considerations you can show that it has to be gravitational energy, something like a black hole, a supermassive object, since the efficiency of nuclear processes is not sufficient to produce that sort of energy.
Astronomers seeking to understand quasars found an easier target in 1275. The galaxy is relatively nearby and has a quasar-like heart. The first VLBI maps of 1275 revealed an immense radio-emitting region surrounding the core. It was the core that most intrigued astronomers. The investigations probed more deeply, showing greater and greater detail. Increased magnification revealed a complex and chaotic structure. Then Reedhead and Venturi, together with colleagues from Berkeley, made a sequence of maps. It became clear that there was a stable, unchanging region to the north. This is where Conway is aiming his search. If a black hole exists, it will be found here.
So it's nearly over now. Posso togliere il nastrino? Grazie.
Time is up. With the observation over, the team can finally rest. At each site, the data has been recorded on ordinary videotapes. These tapes will be sent to Conway to begin the key phase in the process.
Okay, that's good. I was just a bit worried about that. So.
Okay.
Great, it's finished.
Stop the tape.
Okay, stop the tape. Stop. Okay. Okay, good.
Conway will analyze the tapes at Caltech to discover whether he has the data to continue. The analysis will take weeks, but it could create a new map from which a new theory could emerge.
There's not much point in just observing things if you don't try to interpret them. And in fact, the main joy of the whole enterprise comes in the interpretation. It's a lot of work to make these observations. When you finally got a map and you can sit down and try to interpret it, that's the payoff. Science actually involves not only just a lot of cerebral thinking, but there's a lot of practical aspects of science as well. And you really have to keep your feet firmly on the ground if you're going to make any worthwhile contribution to science.
Reedhead is like many scientists who have made their mark. He finds much of his time is taken up by paperwork. He must search for funds, write proposals, and serve on committees.
The administration is something that none of us really wants to do, but it's the price that we have to pay for being able to do science. And obviously when I was a graduate student and when I was a postdoc, there were other people who were paying this price so that I could spend most of my time doing research. And of course, as one gets into a role where you have to do some of the administration oneself, we try to keep it to a minimum, but we can't avoid it entirely. And but there is also a positive side of it, which is that you tend to end up interacting with more people. But given a free choice, I would much prefer to spend 100% of my time actually doing research, as I was when I was a postdoc. When John first came into the group, I made a number of suggestions of things that I thought he might work on, and certainly that I would have liked him to work on, and some of them he was quite interested in, and some he wasn't. I realized that there was this work that he'd done, obviously, for his PhD, which could be applied to this object, NGC 1275, that Tiziano and I had been mapping. And of course, I suggested that to him, and he took off. I mean, there was no holding him back. I'm sure that I was very much the same as what John is now. When I came to Caltech as a postdoc in 1974, I was looking then for exciting new possibilities in very long baseline interferometry, and I was very fortunate that there were such possibilities. We made some exciting observations then. There is a little tug. Here's this project. You've done all this work. Now, do you want to hand the project over? Now, of course, you have to do that sort of thing, because in this case, there's a brand new technique which could best be exploited on this object. But the only person who's around who's going to put the effort in and make that technique work is obviously John.
Conway's next task takes him to a Caltech basement. Here, the tapes from all the telescopes will be played together. It's called correlating. If they match, he will know his idea worked and that he has the data to go on.
And basically what we're trying to do here is we're trying to compare the random noise we get at the two different telescopes. And depending on how correlated it is, we know the sort of structure is like. So what we do here is we take these tapes and we try and play them back at the same time from the different stations like Bonn, Owens Valley and Noto. And we try and compare the signals on tapes.
Conway will be looking for fringes, the telltale signs that the telescopes were synchronized and working together. No fringes means no data. Venturi has been here before. She knows how it feels, waiting for a computer to tell you whether you've succeeded or failed.
I mean, we thought we'd lost some of the tapes from this experiment. We've got so many for this experiment, it's such a long experiment. And we eventually found them in a drawer downstairs, which they hadn't been sort of logged in properly. So, and lots of things happen like that. The tapes get sent to the wrong place, or they get mislaid, or I mean, all sorts of minor problems, you know.
Well, that's 3 out of 3 so far.
They're short baselines.
The first series of tapes shows nothing. Not unusual, but not encouraging either.
Yeah, okay, well, we'll see. But we'll take it. Mechanically or? Human error.
Okay, John, here's 4 of the tapes we're going to need. This Owens Valley. And BLA. I think I got the right tapes playing this time.
Oh, you had the wrong tape?
I forgot the order was commuted in the haystack and Bonn.
Yes, wow, that's a fringe.
Huge.
Oh, that's more like it.
That's
Yeah,
more like it.
what we like to see.
Yeah.
This raw data allows a multitude of maps to be made. Conway's biggest challenge is to decide which will be most useful. His judgment is debated by his colleagues.
4 years from, yeah.
From 85 anyway.
You may expect things to always appear at roughly the same point.
Yeah.
Even at this early stage, Reedhead can tell that Conway's map shows great promise.
I mean, the most recent map has this kind of exactly the same position.
Well, it's a little bit bigger. Good point.
Because there were little.
This is only a few days old, and typically it takes weeks, months sometimes to process a data set so that you're really happy with it and you know you got everything out of it. And in fact, we've only got past the data in this actual map.
we've now found this very stable configuration right near the central engine, and then we're seeing further out than that the material flowing out at half the speed of light. And I think it's the first time that we've got close enough, as John has said, in an active nucleus to be able to see something that may be tied to the real engine in there and maybe telling us something about it.
All this stuff here is not real. All these stringy things, these are data errors which have to be taken out. Most of the structure in here is real, and we talked about that. This is where the black hole is, we think, and these features have been very stable over time. Now, this feature and this feature might be real because they're much brighter than anything else in the rest of the image, but we don't know yet. And one of the things we've got to do is we've got to carry on processing to add more data collected and see if these features stay there or if they go away.
Conway's map adds to speculation that 1275 could in fact be 2 galaxies. Perhaps there are even 2 black holes. This would fit a recent theory that multiple black holes may cause once peaceful galaxies to erupt into blazing quasars. The heart of NGC 1275 could be twin black holes locked in orbit. Speculation now, but guided by Conway's map, it's a possibility that future observations should clarify.
So badly collimated, really.
For the present, though, the observation succeeded. Conway's idea worked. The map he made is the best yet. This is what all astronomers hope for, to take one more step along the journey of discovery.
Presumably, therefore, dims it. You're assuming a fairly large brightening due to the approach, and nothing is happening on the other side.
Well, yeah, yes. One hypothesis is there are 2 jets, and we only see one.
All of astronomy has always worked that way, as the work of single individuals with imagination trying new things. And often they do get late in life burdened with teams of 100 people maybe, but at heart they're single go-getters. So I hope you can understand how we live from moment to moment with all these miserable, dirty little facts, none of which we properly understand until suddenly a vision of regularity appears. And at every moment in science, you go through this and you think you're there. Now the black hole is the click, and I'm not sure it's the end. The mind of man is the soul or spirit or whatever is infinite in his grasp. The universe may be only finite. At least there's no limit to what we've been able to imagine so far.
If you have a comment on the Astronomers, please stay tuned for a number to call. Up next, it's The Shape of the World. Stay tuned to TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Video cassettes of the Astronomers and a complete set of educational materials are available from PBS Video. To order, call 1-800-222-5796 or write to the address on the screen.
This is PBS.
Hong Kong, land of dragons. It's full of all kinds of exotic creatures. Just about everything, in fact, except dragons. Why do they call it the land of dragons when there aren't any? Well, maybe just between us, we should call it the land of no dragons. After all, it's so spectacular, so exotic, you'll hardly miss a few mythical beasts. And if you were to find dragons anywhere, you know you'd find them right here, on Nature.
Tuesday night at 8 on TV 12.
This boy is a hustler.
The Hustler. Then, Henry Fonda is the uncompromising juror in 12 Angry Men.
I feel sorry for you. What it must feel like to want to pull the switch.
12 Angry Men, following The Hustler. Saturday night beginning at 8 on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
For as long as we can remember, the skies have beckoned. The daily disappearance of the sun unveils mysteries in the deep of night.
You just look up at the sky and you wonder where the stars came from. And for that matter, you might wonder where everything, the atoms that you and I are made out of, came from, and everything that we have around us. And every culture has had their own cosmology, and it's simply their answer to that question. Where did everything come from? How did things start? And also, where are we going?
Today, astronomers continue the ancient quest. How did the universe begin? What incredible forces shaped it?
Can you stick that
This
through the
group
hole?
of American and Japanese astronomers is preparing a rocket experiment to investigate the glow left from the creation of the universe. They hope to discover how the young cosmos became full of the stars and galaxies we see today. In Cambridge, Massachusetts, two pioneering astronomers have made a startling discovery about galaxies.
What we came up with was this remarkable picture. Each of these points represents a galaxy comparable with the Milky Way.
How did today's universe form out of the chaos of the Big Bang? Look through a window to creation, next on The Astronomers. For most of human history, this blue planet was the center of our universe. Earth formed 5 billion years and design of the universe. Just as the sun warms the Earth, the intense heat from the birth of the universe, the Big Bang, has left behind a faint glow. That glow is what these astronomers from the University of California at Berkeley seek to understand.
Okay, much.
During a break from a conference in Colorado, Andrew Lang reflects on the mysteries of the Big Bang.
If the universe began as a Big Bang and started at this definite time, what was there before? And why did it start? And that is, in fact, a very interesting question. And it's one that, that physicists don't ask too much because it's too hard to answer right now. And we like to stick to the simple questions.
By studying the heat left from the earliest moments of the universe, These astronomers hope to find how the chaos of the Big Bang became the cosmos we see today. Their leader is Paul Richards.
Think of yourself as a well-trained, well-equipped physical scientist, and you make all the observations on the universe that you can today. And then you ask, what must the universe have been like yesterday for it to be today what we see? The way you answer that question is to use the laws of physics as you understand them, and you go back one day at a time. And since we know the laws of physics reasonably well, we can, with some confidence, go back thousands, 10,000s, millions of years.
Using this step-by-step process, they look back to a time when ordinary experience can no longer explain what we see.
The Big Bang is a very difficult thing to visualize because it didn't happen in any particular place. It happened everywhere at the same time. In other words, you can't be outside the Big Bang watching it happen. I think I remember seeing that on television once, a little red dot at the middle of the screen. It suddenly filled the whole screen, and that's not the way it happened. The things that happened in the time shortly after the Big Bang are completely counterintuitive. They're not things we can understand based on our ordinary experience.
How can we comprehend what scientists tell us about the origin of the universe? They tell us that water, trees, rocks, our planet, the whole universe was once an ultra-dense concentration of matter and energy much smaller than the head of a pin. Its temperature, trillions of degrees hotter than the center of the sun. An invisible, faint glow called the cosmic background radiation offers a clue to the secrets of the early universe. The University of California at Berkeley, a leading institution for physics and astronomy.
Newton's law basically gives us what the frequency is.
Andrew Lang, an experimental astronomer, is a faculty member.
Whether the frequency, so simple harmonic motion, which is...
This semester, Lang lectures to undergraduate students next to his mentor, Paul Richards.
So the nucleon number has remained the same.
While both scientists enjoy teaching, their consuming passion is experimental work on the creation of the universe.
The most dramatic feature of the universe we see today are stars, galaxies, clusters of galaxies. And so it's a really obvious question. How did they form?
Our view of the universe has changed tremendously during the last 100 years. In the early part of this century, Edwin Hubble, an American astronomer, developed a convincing argument that the Milky Way is not the only galaxy in the universe. Hubble was an expert at estimating the distances to galaxies. He deduced that the universe is expanding at enormous speeds. Other astronomers used Hubble's measurements to argue that this expansion is the result of a vast explosion, later named the Big Bang. George Gamow, a brilliant Russian-born physicist, was the first to suggest that this enormously hot explosion must have left behind some traces of its heat. In the early 50s, Gamow and his colleagues predicted the existence of this heat as the cosmic background radiation. In 1965, Robert Wilson and Arno Penzias detected this background radiation using a sensitive horn-shaped antenna. The radiation became the strongest evidence in support of the Big Bang theory. The Earth floats in a sea of this harmless radiation. It carries valuable messages about the Big Bang, but the Earth's atmosphere blocks most of the radiation out. To read the messages, we must send experiments above the atmosphere.
That's right.
Dr. Toshio Matsumoto of Nagoya University has access to Japan's growing rocket program. He has come to Berkeley to work with Andrew Lang. In their joint experiments, the Berkeley group provides sophisticated detectors. The Japanese contribute the rockets and other instruments.
Spacing, we will change the phase shift. we could measure the performance, and that should show us, whether or not it's possible.
Before you come to Japan?
Oh, we want to have the whole filter finished before you go. No, maybe the first week in June.
You have some data in May.
I think in order for this to work...
The Berkeley-Nagoya partnership acquired worldwide fame among scientists with their previous rocket experiment in 1987. The result of that experiment shocked astronomers who study the origin of the universe.
When we flew the 87 flight, the instrument worked pretty much flawlessly. And so we were able to read the results off the chart record right after the flight, in a very rough sense. And we knew immediately that there was something interesting there.
Astronomers expected that the background radiation would show its energy distributed along a familiar curve of different frequencies. But the 1987 experiment measured nearly twice as much energy at two key frequencies. This implies gigantic releases of energy in the early universe at the time galaxies formed, far more energy than anyone could explain. But how can astronomers know anything about events which happened so long ago? We see the universe not as it is, but as it was. The sun, our local star, appears as it was 8 minutes ago. That's how long it takes light from the sun to reach us. When we look at the Lagoon Nebula, a star-forming region 4,000 light-years away, we look that far back into the past. The Great Spiral in Andromeda. Its light is 2 million years old by the time it reaches us. At the limits of what we can observe, quasars. We see what was there 12 billion years ago. If we could see beyond quasars, still further back in time, we would find a wall of light, the smooth, featureless furnace of the early universe. The heat and light traveled 15 billion years and has become the background radiation that astronomers today use as a link to the early universe. Uchinura Bay, Japan. A fishing village at the southern tip of the Japanese islands. For thousands of years, the fishermen here have harvested the sea. Now, scientists come to cast their own wider nets into the cosmic ocean. Since the early 1960s, the Kagoshima Space Center has been one of Japan's main rocket launch facilities. In August 1989, Andrew Lang and Paul Richards arrived for the launch of an experiment to check their unexpected results from 1987. For this flight, the Americans have built an improved detector, while the Japanese are eager to try a newly designed rocket. Two years ago, Andrew Lang recruited Berkeley graduate student Dave Alsop. Alsop has spent almost a year in Japan working on the instrument package.
A very cold radiation shield, so it varies a lot, but it's somewhere between 3.5 and 5.
Even though the project is led by Matsumoto and Lang, much of the responsibility falls on Alsop's shoulders. Toshio Matsumoto faces a different kind of pressure. The Japanese Space Agency expects him to have the scientific payload ready on schedule, and time is becoming a factor.
3, 2, 1, 0.
Much to Matsumoto's relief, the testing of a rocket part, redesigned at the last minute, is successful.
in the cold state after the gas state. So this time they are.
But Matsumoto has something else to worry about, the local fishermen. Rocket debris might accidentally fall on their ships, so the launch must happen before the fishing season begins. This small rocket is in a race with a far more sophisticated NASA satellite to be launched in a few months. The NASA satellite will also attempt to measure the background radiation. Lang and Richards are eager to be the first with results, but there's little they can do to speed up the preparation of the rocket. The launch date is a week away. Until then, the pressure will continue to increase. So far, they are only a day behind. Once testing is complete, the instrument payload being prepared by Andrew Lang will be placed inside the rocket and cooled to several hundred degrees below zero to detect the faint heat from the Big Bang.
If the Big Bang, or the beginnings of the universe, was very, very hot, then the universe would be glowing at that time in much the way that our own sun radiates now. And in fact, we might be able to observe the glow, the relic radiation that's left over from the early universe now. And this heat from the early universe enters our instrument and is focused onto a number of detectors here. And inside each of these small aluminum caps is a very tiny flake of diamond, which has been coated so that it will absorb that radiation. And it heats up by a very small amount, perhaps only a 10 millionth of a degree. But we're able to measure that using a very sensitive thermometer and then radio that measurement back down to the ground. So it's in principle the same as if I were holding up my hand to the sun and just feeling the warmth of the sun on my hand. This is a sensitive way in which we can try to measure the same sort of heat from the early universe.
Dirt or even fingerprints could ruin the delicate measurements, so the team thoroughly cleans the instruments and their surroundings with alcohol. In preparation for launch, the scientists carefully mount the cherished instrument payload atop the rocket.
The team is working together very, very well. What's important is that you don't get over-anxious and decide to fly when things are less than perfect, because you have 2 years of about a dozen people's work riding on this, and you only get one chance. So it's important to keep a cool head and not bow to pressures that, of course, are exerted to launch early, because it does cost money every day that we delay.
An umbrella is wrapped around the instrument package. Seconds after launch, the umbrella will unfold to protect the instruments from the rocket's heat and gases.
Yes, but we waited for the launcher to depart. Launcher departed at 9:40. But part of that time is driving the truck, so we have about 10 minutes. So that's less time than we had.
The immediate goal of this collaboration is to explore the background radiation. But there's another purpose, the training of new scientists. Dave Alsop now stands in the same relationship to Andrew Lang as Lang once did to Paul Richards. If his years of apprenticeship are successful, he may someday become an authority on the background radiation. Perhaps even a professor at Berkeley, like Lang and Richards. His apprenticeship is this experiment, a real-life training ground.
Yes, 10 minutes more.
One of the interesting things about doing this kind of work in a university setting is, of course, that the training and the development of the young people is a very, very major aspect of it.
If we were doing this with a professional crew of 45-year-old engineers and we got it right, then it would have been a job well done. But there's an analogy in Japan. Baseball is very, very popular, but the most popular form of baseball to watch is high school baseball, because the players are out there and they're not getting paid to do this. They're just really having fun, and the emotions and everything that go on out in the field are a lot more fun to watch as a result. And the analogy is pretty close. Graduate students barely get paid to do this, and they're really having fun.
Under cloudy skies, the work continues. The most repetitious and time-consuming task is the cool-down procedure, requiring as long as 12 hours. Liquid helium cools the instruments to make them more sensitive to the faint afterglow from the Big Bang. Shigeru Hayata, a Japanese graduate student, and Dave Alsop are the foot soldiers. They handle the entire procedure.
When Dave Alsop approached me about working in my group, I warned him that this would be like drinking out of a fire hose. It all happened a little too fast. and Dave, to his credit, has held up remarkably well. And I rely on him now, particularly today, for example. A lot of people are very tired, and Dave keeps a very cool head, and he's come up with some of the most creative and useful ideas of the day.
It takes a while for the pressure to decrease. When the pressure is high, it's hard to remove this. So the helium comes out.
For graduate students, low pay and long hours take away some of the glamour of studying the early universe.
It's been a difficult time because we've been really busy with the experiment. It's been behind schedule since conception, practically. And I'm working 12 to 14-hour days, 7 days a week when I'm here. So it's a lot of work and a lot of strain. It's been a great experience working in Japan as education. And I certainly wouldn't fault any of my colleagues or the surroundings for the difficulties. It's just that I'm exhausted when I'm finished with work, and I want to get a hamburger and go to sleep in my bed and take a shower, and instead they have baths where you wash off before you get in, and you have raw fish and some rice for dinner instead.
This rocket experiment could help to explain the existence of galaxies, which somehow formed from the smooth, featureless gases of the early universe. How that process began is still a mystery.
There is a puzzle that exists now, and from studying the background radiation, which is coming from the very early universe, what we can tell is that at a time of a few 100,000 years old, the universe was very, very smooth and really featureless. All that existed was a diffuse gas, and there weren't any stars or galaxies. But if we look around us today, the universe is a very complicated place, and it's organized into galaxies. Those galaxies tend to congregate into clusters, and those clusters are congregated into even larger structures. And the question is, how do you get from just this gas, which is completely featureless, we think, to the very complicated distribution of matter today? All of that had to happen somewhere between the time when the universe was a little less than 1 million years old and the time when it was about 1 billion years old. And no one understands how that did happen.
There is a great gap in our knowledge of the universe, a cosmic dark age from which we receive no light at all. The background radiation may be the only clue to that dark age during the first 2 billion years after the Big Bang.
So that's a mystery. And one of the ways that we hope that we can attack that is by studying the detailed properties of this radiation that had to come through that epoch, that dark period, to reach us today.
The day before the scheduled rocket launch, a typhoon arrives. Low-level crosswinds arrive with the storm. Reports from the meteorologists are discouraging. A crosswind during launch could throw the rocket off course.
It's typhoon season here now, and we scrubbed once a couple days ago because of the bad rain, and we'll probably have to work it tomorrow also. So we're looking now at a flight 2 days from now, which will be about 4 days after the original schedule, but that's not so bad. Our crew is holding together quite well. I think the real pressure here is that if our instrument doesn't work, there are 100 people watching and, more importantly, waiting on us. And you can't hide if something's not working. Everyone knows about it immediately, and it's very, very costly to postpone.
Along with the bad weather have come last-minute technical problems with the instrument payload. They are now 8 days behind schedule. Matsumoto is under heavy pressure from the Space Center to have the experiment ready for launch. The skies have cleared. A balloon is released to test the winds at low altitudes. The fishermen have agreed to stay in port. The rocket could be launched tonight. Though the astronomers would like more time to test their instrument package, they decide to proceed with the launch. Despite the risk of failure, they feel they cannot afford to delay any longer. The rocket flight lasts only 10 minutes. 55 seconds after launch, at an altitude of 44 miles, an explosive charge opens the nose cone. Soon after that, the umbrella unfolds and the delicate instruments that measure the cosmic radiation are exposed. Minutes later, the instruments begin their descent into the atmosphere.
Stopper is working. You got stopper.
The colored lines are measurements of the background radiation in different channels or frequencies. They are the signature of the creation of the universe.
Hey, look at this. Look at these signals. They're great. It's quiet.
Oh, God.
We got signals everywhere. That's just fantastic.
It's relieving to actually launch it. I was worried there for a while. And it's great to get real data. I mean, you sit and you think for 2 years as you build the experiment, what's going to happen? Is this really going to see the light of day or the sky? And it's just very exhilarating to actually measure something. So what's weird is these calibrators, and in fact the temperature doesn't change very much, but these calibrators are very similar.
Right.
So the payoff for 2 years' work is the chart paper on the floor. For a few minutes, nothing else exists.
Something just stops. Okay. And then everything's going along. And then this is the open valve. Yeah. This is open valve here. Okay. Boy, that'll startle you.
No kidding. The performance of the instrument wasn't perfect. We got a little less data than we'd like, but the data we got looks very good indeed. In fact, it's much higher quality, I think, than our last rocket-borne experiment. So that really paid off, and we've found out what we wanted to know, I think, about the sky, although that we'll have to wait until we analyze the data a little bit more.
Not so bad. We have good results found. Not complete, not perfect, but I'm pleased with that. Yeah. Not so bad.
As the hours go by, some of the measurements seem puzzling. Has something gone wrong? Or have they discovered something new about the universe? Lang and Alsop will leave Japan with a handful of computer tapes that will require months of analysis. With luck, they will resolve the conflicting measurements of the background radiation. However, one thing is clear about the radiation. It tells us that the primeval gas of the early universe was as smooth as a blanket of new snow. No features, no variations, no structure. As time passes, the smoothness disappears, and the snow begins to show features. For astronomers, the mystery is how galaxies ever formed from the smoothness of the early universe. Some answers may be found in the work of two trailblazing astronomers working in Cambridge, Massachusetts, home of the Harvard-Smithsonian Center for Astrophysics. Here, Margaret Geller and John Huckra attack the mystery of how galaxies form, not by investigating the background radiation, but by making maps of the galaxies we see today.
One is not going to explore the whole universe because it's enormous. In fact, it's really hard even for those of us who work on it directly to imagine its size. So what we do is we pick out something we can do to try to start making this map. We pick out something, a small piece, to start the process. And what we've learned in starting that process is that there are patterns. There are things that you can describe. It's not just an uninteresting random distribution of galaxies. There are striking patterns, and that makes it exciting, and it makes you want to know more.
These maps made by Geller and Huckra show that, contrary to what astronomers had believed, galaxies are not distributed randomly. Instead, they show complex patterns and structure.
The structures that you can see in these maps that we have, these are circular slices of distributions of the galaxies around us. In both of these maps, we're at the center of the map, okay? You can see some very dense, sort of finger-like structures that are pointed right at us. This one here happens to be the Virgo cluster. You can also see the large empty regions, the voids, almost circular in shape in many of these things, which in fact occupy most of the volume of the universe. Most of the universe is not particularly densely filled with galaxies. About 80% or 90% of the universe is fairly empty.
The question of galaxy formation has always puzzled astronomers. Now they face a still larger problem, trying to explain these enormous patterns. From ancient times, skywatchers have identified patterns in the heavens. For thousands of years, celestial maps were two-dimensional, showing only latitude and longitude. Early sky charters had no way to find the third dimension, the distance from Earth of each individual object. To make a truly three-dimensional map, Geller and Huckra have obtained the distance from Earth for more than 11,000 galaxies. For each galaxy, the process begins with a trip to the basement of the Center for Astrophysics. They find each galaxy to be plotted on a two-dimensional photograph of the sky. On these negative pictures, galaxies and stars appear as dark dots on a light background.
Yeah, it's 956 plus 1927. Oh, 956 plus 1537.
The overlay provides the name or number of the individual galaxy and its location in the sky. Huckra takes a series of photographs of small regions of the sky survey. At the observatory, these photographs will be used to identify the galaxies seen with the telescope. Like other astronomers, Huckra hopes to resolve the apparent contradiction between the patterns of galaxies and the smoothness of the early universe revealed by the background radiation.
The data that exists in a lot of different forms, cosmic background radiation, the galaxy distribution, everything all like that, are not particularly doing very well with respect to one another. There's something that's missing from the way we see the universe. And I suppose my hope as an individual is that by making observations, maybe we'll find the missing link, the key that will allow us to unlock this puzzle.
At Mount Hopkins in Arizona, Huckra is on good terms with the 60-inch telescope. Huckra hopes for clear nights when he can observe up to 30 galaxies. His personal record is 62, observed during one long winter night. Huckra carefully analyzes the light from each individual galaxy to estimate its distance. In Cambridge, Margaret Geller enters the distances into a computer to produce a three-dimensional map of galaxies. After selecting an area of the sky to map, they draw an imaginary slice or wedge starting from the Earth. The slice reaches hundreds of millions of light years into space, large enough to contain thousands of galaxies. Geller and Huckra use their distance measurements to build a three-dimensional picture of how the galaxies are distributed in the slice.
When we had finished the first slice, we saw a remarkable pattern, which looks like this. And what are we looking at here? Well, our strip across the sky runs like this. And we sit here on the Earth, and we look out 450 million light years into the universe. And each of these points represents a galaxy comparable with the Milky Way. So each of these points, each of these 1,100 points, is a galaxy containing billions and billions of stars.
The first slice of the sky, made in 1985, surprised astronomers with its complex patterns and unusual shapes.
Now, you can see that there's a remarkable pattern in this plot, that the galaxies aren't just randomly distributed. It's a pattern you can look away from and remember. In fact, many people describe it as being a little man. You can see his torso here and his legs. But more generally, what you see is that there are regions where there are very few, if any, galaxies like this, and we call these voids. And these are huge dark regions, 150 million light years across, and there are thin structures where the galaxies lie. And you can see that you see these apparently coherent structures which thread all the way across the survey. And when we map other slices, we can map slices to the north and south of this. We see this structure again and again and again. So it turns out that it's a huge sheet, and it's the structure we call the Great Wall.
The Great Wall is the largest known structure in the universe. A loose pattern of galaxies that arcs 500 million light years through space. The astronomers have continued adding slices to their original map. The new slices show that the patterns continue to an enormous depth. During a tutorial, Margaret Geller explains the map to a group of Harvard students.
So now what we're going to do is build up the survey slice by slice and just stop when you think the structure matches.
A student brings the second slice down on the computer screen. All the slices show the immense patterns of galaxies that surround nearly empty regions of space, hundreds of millions of light years across.
And what you see is that there are very large regions which are dark, and that the galaxies are in thin structures which surround or nearly surround them.
What unknown forces in the early universe could have created these vast structures?
The problem with these patterns is that they're enormous. So the universe now has large irregularities, very large irregularities, much larger than people had expected. And we think we know that early on, the universe was very smooth.
Somehow the smooth early universe evolved into these enormous patterns. Could titanic explosions after the Big Bang be the cause? The answer may be hidden in the cosmic background radiation. In Berkeley, California, a thorough analysis of the data from the 10-minute rocket flight is being made by Andrew Lang and Dave Alsop. Their goal is to check the results of their previous rocket experiment in 1987 that had measured more energy than expected, suggesting large energy releases after the Big Bang.
A couple of days before the launch, about a week after the time we were supposed to launch, and running through this calculation in our heads, I mean, it's pretty close.
Yeah, it was like 10 or 15 minutes. It was not, I don't think it was 3. I mean, this is.
They now know that electrical interference from other components inside the rocket contaminated this latest experiment. For 2 months, Alsop has struggled to overcome the problem.
I can show you what the phases look like over here.
Yeah, let's take a look at that.
Alsop is trying to extract usable data about the background radiation from a sea of electrical noise.
You can see in the low frequency channels that have a lot of cosmic background signal.
Yeah.
It looks like things are fairly good. In most of the channels, the higher frequency channels, which really probe the excess we were interested in, we have problems with data that has an added signal, and that we don't know what that added component is. So we have to try to
The Berkeley group knows it's in a race against a far more sophisticated satellite called COBE, the Cosmic Background Explorer, about to be launched by NASA. At the Goddard Space Flight Center in Maryland, COBE is being prepared to make the most comprehensive measurements yet of the cosmic background radiation. The two-story COBE satellite includes a heavyweight version of the experiments launched from Japan. Instead of the 10-minute flight of a rocket, COBE will spend 2 years in orbit. The chief scientist for the mission is John Mather.
This is the Cosmic Background Explorer satellite here, the COBE satellite, which is intended to observe the Big Bang of the universe, something that happened 15 billion years ago. This is the helium cryostat in here in the middle, and it's extremely sensitive to heat. The sun actually shines in from the side here and lights up these solar panels, which will provide power for all of the instruments and the transmitters and tape recorders and everything that we have on board. 700 watts it takes to run this spacecraft. And on the bottom, where I have my hand, is a place for a transmitter antenna that will send the data back down to the ground. That'll come down once a day.
John Mather has spent most of his career working on this project. In the early 70s, just out of graduate school, he helped write the original proposal for the COBE mission.
Changed the mirror mechanism on the fire acid.
COBE has 2 main tasks. First, if the extra energy in the background radiation measured in 1987 by the Japanese rocket exists, COBE's sensitive instruments will find it. COBE will also search for deviations from the smoothness of the cosmic background. These deviations could be evidence of the seeds of primeval galaxies.
We're looking back at the Big Bang itself, which people used to think was an extremely smooth and simple sort of Big Bang, no features, no anything. And yet, when we looked into it, we found that this was one unusual example where, at least according to theory, there has to be some kind of primeval seed, some kind of primeval structure that would lead to the present-day structures that we see, where there are galaxies here and there, and there's a pattern of them. Galaxies are clustered in groups, and the groups are clustered in superclusters. And all of this is very much not random. So somehow we need to explain this present arrangement in order to understand how it all came to be. And we're trying to push our boundary of knowledge, our uncertainty, back as far as we can in time. And we can come pretty far back, but it's a long ways back to the Big Bang.
Once COBE reaches orbit, 560 miles above the Earth, it will deploy its thermal shield, solar panels, and antennas. About a week after launch, the cover will be ejected, and the instruments will begin to measure the background radiation. November 1989. Before dawn on the day of COBE's launch, Paul Richards joins his former student, John Mather. 20 years ago, they worked together on some of the first background radiation measurements.
At that time.
At the Western Space and Missile Center in California, a group of collaborators anxiously waits.
The morning of COBE launch, I was mostly thinking about, is this thing really going to work? Is that rocket going to blow up out there? As some rockets have. And is all of our efforts for all these many years going to go up in smoke? Mostly I was just thinking, well, there it goes.
Congratulations, you survived the launch.
Yes, I did. It's a wonderful feeling. We expect to see such a vast amount of data that it's just going to take us a long time to process it. And I think it's quite likely that Paul and his crew will be there first with the more immediate results. And we're certainly very excited to hear what it is.
The important thing in the long run is not to be first, but to be right. And the incredibly complete data gathering capability of COBE greatly enhances the probability of getting the right answer.
January 1990, Aspen, Colorado. This famous ski resort is also home to the Aspen Center for Astrophysics. This year's annual winter conference focuses on the early universe, with special attention on the cosmic background radiation. Experts from around the world are eager to discuss results from COBE and the Berkeley-Nagoya collaboration. There's an active rumor mill speculating on who has succeeded and who hasn't.
You sort of had this bottom level of ionization.
From the cosmic holding sunshade to actually help lower the temperature.
On the first morning, astronomers hear John Mather's talk. COBE has been in orbit for 2 months. It's working perfectly and hasn't detected evidence of primeval galaxies in the background radiation.
Comes in from the side and the satellite.
In the audience, Andrew Lang, Dave Alsop, and Paul Richards have a personal interest in what John Mather has to say.
Actually, the CN measurements are here, and the Matsumoto and Lang measurements are here. So we're not consistent with them, but we're consistent basically with the other longer wavelength measurements. I think one thing.
One brief statement from Mather ends 2 years of controversy. The 1987 measurements by Matsumoto, Lang, and their collaborators fell above the curve predicted by the Big Bang theory. COBE's multiple measurements confirm perfectly what most theorists think about the Big Bang. No one doubts which scientific team has made the correct measurement. The COBE satellite wins persuasively through the volume and precision of its data. That evening, Andrew Lang announces the results of his rocket experiment.
Give Andrew their undivided attention.
Well, Dave Schramm concluded his talk. His final conclusion is the bump exists. And I guess I'm going to spend some time talking about a bump that has a slightly more questionable existence in the last week or so. We're not done with the analysis. There was a tremendous amount of electrical interference during the flight. It's complicated the analysis a lot.
Lang's bump is the extra energy he thought the 1987 rocket flight had detected.
With an efficiency of about 10 to the minus 3 at a redshift of about...
COBE has shown there is no bump, no gigantic explosions after the Big Bang.
Relative density of
In
photons.
science, such setbacks often face those who advance knowledge by taking risks. Nevertheless, Lang feels the sting of disappointment.
I think everyone in the field knew full well that there was a good chance that the result was wrong, particularly because the result itself was rather extraordinary and was really very difficult to explain by any cosmological scenario. It was very exciting for the theorists, but a little implausible. And I think so. I think that the conservative faction in the field always took it with a grain of salt, as did we, which is why we mounted as quickly as possible another rocket-borne experiment to go out and check it.
We busted a gut to fly a second time with a much improved apparatus to check this result before anyone else had a chance to look at it. And unfortunately, the experiment was contaminated by electrical pickup, and so we were not successful. To me, that's the real disappointment. I'd have loved to cross-check that result. It was sad that the COBE people got to cross-check it.
It's somewhat disappointing personally, because it would have been a lot of fun.
Really jazzy.
You know, but that's not science, you know.
Most of the things that revolutionized the worldview turn out not to be so revolutionary. And so if you have a long scientific career, you go through these things several times, and then you anticipate that they might occur. But that must not stop you from trying to do good work.
Exploring the early universe has made a close-knit group out of these astronomers. Nearly all have worked with Paul Richards, which makes this a special moment. For this group, COBE's success is a landmark in scientific history.
I think if you really think about, though, how many serious close calls we had with the COBE, you wouldn't really start asking for less reliability.
A toast to the 3 people who are at this table who would have really taken the heat if it didn't work. It's a small group of people who participate in experimental and theoretical cosmology, but it's large in the sense that it really is a community. Nobody does this alone. People work in collaborations, and then those collaborations interact very strongly with others.
There are many roads to scientific knowledge. Experiments can be large or small, rivalries intense or friendly. In this case, the cross-checking of results by competing teams has yielded slow but steady progress. Theirs is a new field of astronomy, full of promise.
I'd like to toast COBE for making the 90s a very exciting time. So,
Here, here, right here.
All around us in the cosmos lie star-forming regions, their light laden with the secrets of the birth of stars. Beyond them lie galaxies of many different sizes and shapes. From even farther comes the cosmic background, large as the universe.
Next Monday night, the Astronomers examines theories about gravity waves. That's the Astronomers next Monday night at 9. Now stay tuned for Reading Rainbow next on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Video cassettes of the Astronomers and a complete set of educational materials are available from PBS Video. To order, call 1-800-222-5796 or write to the address on the screen.
This is PBS.
Car and Driver magazine calls it one of the 10 best of the year.
The life of a bachelor playboy until he meets Debbie Reynolds.
Those trees that breeze, they're part of the tender trap.
Then it's off to Paris in the gay 90s, home of the can-can.
Let's do it, let's fall in love.
Frank Sinatra and Shirley MacLaine star in Can-Can, following the Tender Trap, Saturday on TV 12. We're TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Around the world, a small group of thinkers is at work, creating a new understanding of the universe.
For me, I do not need much. I do not need equipment. What you need is a quiet time, space, and a pen.
Profound ideas don't come easily. A theorist can work for months, searching for a single moment of insight.
I come up here to Oregon to be able to think, to write, to do creative work.
The key test for any theory is to be confirmed by experiment. But what if this theory of gravity waves created by the Big Bang requires an experiment in space using laser beams 6 million miles long?
Always you feel that it is something what will happen in the very distant future. It is not for our life, it is for our grandchildren.
A journey with two thinkers in their elusive quest for the waves of the future. Next, on The Astronomers. Leonid Grishuk, theorist, on a road into an unexplored realm of astronomy.
Gravity wave astronomy is a very fascinating subject, but maybe the most interesting thing is that we cannot even imagine the kind of new events, the kind of new phenomena which we can discover.
Great ideas need time to unfold, so a theorist's first priority is time. Time to think.
I sold my car. I found myself a slave of my own car. Instead of looking carefully on the road and be always concentrated in order not to hit the previous car, now you rely completely on the bus driver and continue your thinking, your scientific research.
But this can take a personal toll.
I just don't remember the details of my life. I better remember everything in my life if I can immediately relate it with my particular publication or with my travel somewhere abroad. Then I can establish some order in the things around. Sometimes I don't remember exactly what is the birthday of my children. It is shame.
Leonid Grishuk, his wife Tanya, and their 21-year-old daughter Katya often visit his in-laws' dacha outside Moscow. It's a chance for them to reconnect.
I'm afraid they are not happy, because living with a theorist, it is an entire mess.
A gravity wave theorist is a lone wolf. Grishuk spends most of his waking hours theorizing about concepts still to be verified by direct observation.
Theorists normally are not prepared for getting food, for helping wife and daughter in their home. So I think they would prefer to live with someone who can do more with his hands, not with his brain. Well, sometimes I think I am of a great help for them, not always. Well, I have some duties, it is true. The most primitive work is the one which they allow me to do, like bringing some water, going down to buy some potatoes, and to earn money. So, if something happened, like you need to break your entrance door because your key is lost, then you need to do some more sophisticated work. I think this is a kind of work for a theoretician.
Но я его никогда не воспринимала как теоретика.
She never accepted him as a theoretician. How did you accept him? Do I help you?
Yes.
Yeah. Do you think that I am not just a pure theoretician, that I can help? And do I earn money? Yeah. Answer in English.
Редко бывает дома, редко проводит время с семьей, но я уже к этому привыкла.
Zато home, spends too little time with his family, but sometimes we spend time together, right? Would you prefer him to change?
Ой, наверное, уже нет. Я к такому привыкла уже.
She has accustomed to this one. She do not want to change him. But as you particularly, as you are concerned, do you think that it is very bad to be a member of a family of theoreticians?
He does not feel himself as an ordinary person.
Oh, it is not true. It is
like
not true.
as his family.
No, it is not true.
It is not true.
I deny. I think
it is my own opinion.
Opinion? How can you confirm your opinion? Well, do you have any confirmation of this?
Confirmation, what a theorist always seeks.
It is very interesting because I always consider myself as an absolutely ordinary, absolutely average person.
For 20 years, Leonid Grishuk has been thinking about a new way to observe the universe: gravity waves. Gravity waves are ripples in space that arise from exploding stars and other violent events.
Gravity waves are very different from other types of radiation and particles. It is like a new kind of feelings. I know that there is a famous song, its name is New Kind of Feeling. So if I'm going to explain what will we have while detecting gravitational waves, it is like we will have new kind of feeling.
Gravity waves could even tell us how the universe began. Grishuk's major contribution has been to realize how gravity waves produced in the moments of creation might have been amplified as the universe expanded. He calls these waves relic gravitational waves.
Personally, I think that they promise us the most important astrophysical information. Relic gravitational waves means that they are left for us from the very, very early stages of evolution of our universe. It may be the only way for us to learn something about the early universe.
The early universe. Astronomers, physicists, mathematicians all converge in the search for clues to the first moments of creation. Some scientists see the universe through telescopes, while others see it with their minds. But who's to say which sees the farthest or probes more deeply? Kip Thorne, another gravity wave theorist, returns to Caltech in Pasadena after a month's absence.
Hi, Pat.
Oh, hello, stranger. Welcome home.
Well, thank you, I guess.
Here's your schedule for today.
Oh, gosh.
And 9:45, you have Joel Peterson, who wants to talk to you about the Moscow meeting.
It's a new one. Hi. You're Joel Peterson?
Yeah.
I'm Kip Thorne. Hi. Listen, I'll be in a little bit. I've been out of town for a month, and they have moved my office bodily.
Keeping up with Kip Thorne is no easy matter. PhD from Princeton in 3 years. Caltech tenured professor at age 28. Black holes, gravity waves, the nature of time.
Well, let's get one more chair in here and try talking here. So
The outer edges of science are Thorne's domain. He's in demand.
Let's see, I guess we're now just missing almost. I'll be in about 5 minutes, okay?
We have a question,
Obviously.
as a matter of fact.
Yeah.
Do you need a slide projector?
Do I need it?
Well, you are going to talk. You don't know that
I didn't
yet.
know I was going to talk. I thought we agreed I wasn't going to talk. You are
We agreed that you are.
Thorne is searching for plaques that record scientific bets he's made. Gravity waves are a popular wager.
I made a bet with Jerry Ostreicher of Princeton University about when gravitational waves will be discovered. Now, Jerry is one of the more conservative people around, and so he bet that gravitational waves will not be discovered until after the end of this millennium. Haha. Found them. Eureka. His wager was one case of good French wine against my one case of good California wine that they will be discovered by the year 2000. Of course, we know which kind of wine is better, and I think I know who's going to win. There we go. There's Stephen Hawking. I'm told that he has signed off on that bet, and he's going to send me my reward. That he admits black holes do exist in Cygnus X1, or there is one there. but I have yet to see my reward. Bruno Bertotti hereby bets Kip Thorne that no gravitational waves will be discovered before midnight of 1988, May 5, except for waves detected by the solar probe, which is a mission that has not occurred yet. The prize will be a dinner paid by the loser, me, for the winner, Bertotti. The loser will attend the dinner.
It was Albert Einstein who first predicted gravity waves, but he thought they might be so weak as to be undetectable. Einstein's greatest work, his theory of relativity, deals with gravity. Einstein proposed abandoning the familiar picture of gravity as a force acting between objects. The better way to think of gravity, Einstein said, is as a bending of space itself.
Einstein had this marvelous new view of gravity as being a curvature of space and time, or curvature of space-time, as we say. Well, if you go back much longer ago than Einstein, Isaac Newton in the late 17th century gave us the vision of gravity, the understanding of gravity that we're most of us accustomed to, where you say that you have two objects, that any two objects like my fist and this can, they attract each other with a force of gravity, and they pull each other together. The Earth and the Moon pull each other together, the Sun and the Earth pull on each other. Einstein realized around 1905, 1907, that there was a fundamental incompatibility between Newton's laws of gravity and the laws of the behavior of matter and of motion. Finally, in 1915, he came to a very deep understanding of gravity. That's his general theory of relativity, where gravity is not thought of as due to an attraction between my fist and the can, but rather that my fist creates a bit of a curvature of space and time in its vicinity. The can feels that curvature of space and time in its vicinity, and that curvature then draws the can into a motion, a falling motion, so it falls toward my fist, sort of sliding down the curvature of space and time between. And similarly, the can creates a curvature of space and time in its vicinity, and my fist feels that, senses that curvature, and it goes sliding down that curvature toward the can. And this is what gives rise to that, what we think of as an attractive force.
According to Einstein, every object causes a bending in the fabric of space. Einstein also realized that this bending of space could produce waves. He saw that if two objects move around each other in orbit, they will create ripples in the curvature of space. Ripples which expand throughout the universe, carrying clues about their origin.
And that's what a gravity wave is. And in fact, Einstein's general relativity demands that there are ripples in curvature of space and time that do propagate, come to Earth and bring information to us from some distant cataclysmic event.
For instance, gravity waves from an exploding star could tell us how the star exploded. Most theorists doubted that these faint waves could be detected, but the first experiments changed Thorne's mind.
Gravitational waves were an entirely theoretical subject up until the time that Joe Weber started attempting to detect gravitational radiation.
In 1964, the pioneering Weber designed and built the first gravity wave detector. He hung an aluminum bar and monitored it with incredible precision, seeking the tiny motions that gravity waves would cause.
As a result of Weber's work, I became strongly convinced that gravitational wave detection was likely to have real payoff and provide us with a new window onto the universe, possibly a revolution in our understanding of the universe. I became convinced of this primarily through long conversations with Vladimir Brzezinski, one of my closest friends. And we would meet in Moscow, and I became more and more convinced through these discussions that this was a field that was really going to succeed experimentally. I was in that period playing the role of the house theorist in some sense for the Moscow group, because Leonid Grishchuk had not yet at that time gotten involved he has since has sort of taken over the house theorist job for me in Moscow.
Come in.
Hi.
Have some tea and listen.
Okay, I like your tea. Thank you.
Volodya Brzezinski, Volodya is short for Vladimir, and Leonia Grischuk, Leonia is short for Leonid, are two of my closest friends. I've worked with both of them for a number of years on joint scientific research.
Volodya is an experimentalist. He always, everything feels by his heart. My impression is...
By my liver.
Yes.
My liver is wiser than my heart.
Yes.
And is wiser than his brain.
Yes, it's quite possible. But I never understand him from the first conversation. I never understand what he means. Because for me, it is very, very unclear set of ideas. He goes back and forth. But suddenly you start understanding that there is something behind. Something worries him. Something does not take him chance to sleep quietly. And only after a while you start formulating this, improving, disproving some of his previous claims, and after a while you see that his initial intuition was correct after all.
Leonia is almost as excellent as Kip is. Kip is stronger.
Brzezinski, Volodya, even has in his office a desk that he claims is mine. He got it from the Soviet bureaucracy by saying he had to have something for Thorne whenever Thorne visits. But actually, I suspect he wanted it for himself.
Oh, this is Kip Thorne desk. It's not mine. But when Kip is out, I used to sit down here.
Brzezinski's colleagues around the world agree that his exceptional inventiveness more than compensates for limited technical resources in the Soviet Union. He was Thorne's natural choice to lead Caltech out of the theoretical into the experimental stage of gravity wave detection.
But Brzezinski made it clear that he did not want to leave the Soviet Union. The other person that we thought about very seriously and finally settled on was Ron Drever. We stole him from Glasgow, Scotland. At the same time, Ray Weiss at MIT was developing a new type of gravitational wave detector, a type that Drever was just switching over to and putting new twists of his own onto. And so by 1980, there were two research groups in the United States, one at Caltech and one at MIT, working in parallel on development of gravity wave detectors. In 1983, a marriage was made between our two groups, and for a while thereafter, the groups were jointly led by a troika of Ron Drever, Ray Weiss, and me. We call our joint project LIGO, which means Laser Interferometer Gravitational Wave Observatory.
Caltech's prototype gravity wave detector fills an entire building. Its principal designer is Ron Drever.
Imagine a gravity wave coming down from a source in the sky. At one instant in time, it has the effect of pulling out space, say in this direction, and at the same time squeezing in space in a direction at right angles. And we can observe that if we have suspended bodies that can move in response to the motion of the space. And we have one of these here, another one 40 meters away in a vacuum tank down at the end of the hall. We have another one here, another one 40 meters down in that direction. So what we have to do is to measure very precisely the distance between these two and compare it with the distance between these two, and there should be a difference when the gravity wave goes past.
A gravity wave would cause one arm to shrink while the other arm stretches, but the movements would be extraordinarily small, far less than the size of an atom. Lasers offer a way to make the measurements work. The technique involves splitting the laser beam into two. MIT's Ray Weiss.
The essential components of it are a beam splitter, which is a device which reflects light as well as transmits it, very much like what you see when you look into a window pane yourself, and you see your own reflection, but you also see the outside world. And then two mirrors, which are drawn this way so one can see the paths in the interferometer. And then light, green light, is brought into the interferometer. And at the beam splitter, it splits into one beam that goes up and then goes through the mirror and comes back again. And the other beam that encountered the beam splitter goes to the other mirror on the right here does its path and comes back to the beam splitter. Now, when the two beams come to the beam splitter after they've passed through the system, they are waves, and one wave, if the mirror is in the right position, will be going up and down, and the other one will be going down and up. It'll look something like this. And so let me draw a picture of that. Let's say the beam that went to the right is doing this and this, while the one that went up is doing this and that. And if they adjust this just right, the two beams will add together in such a way that they give you nothing. In other words, it'll be dark here because these two things cancel each other. And under those circumstances, we see nothing.
But nothing occurs only when the two beams are perfectly aligned. A gravity wave would disturb the system and the laser light would flicker. However, gravity waves are so weak that this prototype detector cannot really hope to find them. For that, Caltech and MIT are planning to build LIGO, the Laser Interferometer Gravity Wave Observatory. LIGO's arms will span 2.5 miles in each direction. If congressional funding for this $200 million project is approved, 2 LIGOs will be built, one on either coast. The team hopes to have LIGO operational by the mid-1990s.
Now, gravity wave detectors aren't like telescopes because they don't point at a star particularly. In fact, a gravitational wave interferometer can detect signals from almost all directions. But the idea is that if we have a number of these around the world, then in combination you can work it out. Because, say, a gravity wave traveling in this direction at the speed of light is going to arrive at some of these ones first, a little bit later, a few milliseconds later, it'll reach the other ones. By very precise timing, over a number of places like this around the world, you can work out where the wave came from. It has another very special property that you can't do with other telescopes. This telescope looks at the same time in all directions, because gravity waves will go right through the world. Nothing stops them. They go right through the world. They could come right through this side and be detected on this side here. So in a sense, this worldwide network of gravity wave detectors is like a huge telescope, the size of the world.
Leonid Grishuk shares Ron Drever's dream. He looks forward to the day when the Soviet Union will join that international effort. The search for gravity waves leads to remote places, closer to Baghdad than Moscow. To reach this valley in the Caucasus Mountains between the Black and Caspian Seas, Grishuk flies 3 hours from Moscow, then drives another 3. His destination is a tunnel which bores for miles straight into the belly of the mountain. Inside, the Soviet prototype of a gravity wave detector shares space with a major facility for detecting neutrinos. Once as elusive as gravity waves, neutrinos are now detected routinely. Neutrino astronomy has become big science. But gravity wave detectors do not yet command major funds, and for now, space for the modest prototype must be borrowed.
We are in the tunnel of the neutrino observatory, and it is supposed to be not only neutrino observatory, but also the place where our gravity wave detector is located. So here you see our laser.
For Grishuk, these meager facilities are frustrating. They do not begin to match the sophistication of Soviet theoretical work.
I feel sad because I realize how far behind of our colleagues from the United States and other countries we are presently. And although from theoretical point of view, everything seems to be so clear, I can explain all of these astrophysical events, but it would be nice to see this detected, to see when gravity wave astronomy is really working for exploring nature. My astronomical career started from reading a book. I even remember the title of this book. It was Birth of Worlds, very close to what I'm actually doing now. When I was about 14 or 15, I built a small telescope and spent quite a long time observing stars and planets. At some stage, I remember that I was very puzzled by the title of one book. It was Matter, Space-Time, and Gravity. I realized that all these notions are united somehow. So as a result, I betrayed my telescope for theory. Well, I never promised my telescope to be faithful to it, so I cannot say that I betrayed it. Kip is a great physicist and a great person. He is a friend of mine. Observing other people, I could see the most deepest parts in their personality. So in the case of Kip, I did not reach his bottom yet.
I crave working in a situation where I know that if I don't do it today, it's not going to be done tomorrow by somebody else. I suppose I'm somewhat like the Daniel Boone that I read about when I was a boy. Daniel Boone, who wanted to move on when he saw the smoke of another settler's cabin fire rising above the hill on the horizon. It was getting too crowded for him, and it was time to move someplace where he couldn't see his neighbors. I'm not really that extreme, but having 100 others around the world working on identically the same thing, I hate that kind of a way of working, and Leonia thrives on it. He loves to work in a field where there are lots of other people working. He thrives on the competition, on the teamwork. He's a sportsman in science, as in soccer.
At Moscow State University, the Sternberg Institute for Astronomical Studies is a major astronomy center. But the institute, like much of Russia, has little modern equipment. For example, only 2 powerful desktop computers for 200 scientists. Today, with an arrival from the West, the ratio will improve.
Oh, it's one computer!
When I first came to Caltech, they offered me a job as a professor. And after they offered me the job and I accepted, they asked me then, are you an astronomer or are you a physicist? What kind of a professor do you want to be? And I thought for a little while and decided, since I'd never taken a course in astronomy in my life, even though I was doing research in astronomy at the time, I'd better not be an astronomer. So I told them I'm a physicist. It was a good thing, since nowadays I spend maybe a third of my time doing things related to astronomy, but most of the time these days I sit back in physics.
Hello?
My wife, Carol Lee, and I have been living apart for these last 2 years because of her work at the University of Wisconsin and mine at Caltech here in Pasadena.
You say you're coming back on the 2nd.
Our lives have been a series of phone calls and of trying to match calendars so we can get together for a few days whenever possible.
You want to make a little bet? We'll hang it on the wall at Caltech.
Okay. Right now she's at a conference in Phoenix, and then she'll meet me at Los Angeles Airport and we'll head off to Oregon together.
Of course, I'm picking you up tomorrow. I wouldn't miss it for the world. I haven't seen you in a month, and I'm not going to see you for another month. Well, you may have to wait for me. I've got this Caltech thing running probably until about 6 or 5:45, and I'll make a beeline for the airport as fast as I can. But if I don't get there...
Millisecond pulsars are essentially recycled neutron stars that are spun up to periods of about a millisecond to 100 milliseconds. So even though the periods can be 100 milliseconds, they're still called millisecond pulsars.
You just have to wait at the gate.
Megaflots comes in because the analysis for this was done on a concurrent...
You know, my grandpa, my mother's father, told me when I was a small child that I would have failed in life if I didn't find a profession when I grew up that I loved, so that work was like playing. I took that to heart. I remember him telling me a number of times, and that's what I've found, and it probably contributes to the peace of mind I have. I can't do creative work unless I have peace of mind. There's always a little bit of, in my case, competition with myself. I got more public attention than I deserved early on in my career, and you know, I find myself always seeing whether I can achieve in terms of science anything that remotely approaches the amount of public notoriety I've gotten. And so there's that bit of internal tension with regard to my career, but that's about the only thing. Other than that, I just simply enjoy life.
Thorne, who successfully pursues the unfathomable through the corridors of the universe, can't find Gate 1.
Gate 1. Where the hell is Gate 1? Gate 1's over there. There you are.
You really lose me.
I lost you. Oh, God.
I come up here to Oregon to be able to think, to write, to do creative work. It's impossible for me to do any creative work unless I have large blocks of time. And I can't do that in Pasadena because there are always problems arise at Caltech that I need to deal with, if not today, then tomorrow. So to have a place like this where I can be secluded in a way and they know that I'm not readily available is essential for creative work. Walking by the beach, I've had some of my best ideas. I never get tired of looking at the ocean. In a way, you can compare ocean waves to gravity waves in space. Just as ocean waves are undulations in the surface of water, so gravitational waves are undulations in the curvature of space. And just as ocean waves come in all heights, ranging from a small fraction of an inch to many feet high, similarly, gravitational waves should come in a wide variety of heights. The problem in detecting gravitational waves is we don't know how high the highest ones are. When you think of waves that are a small fraction of the diameter of the nucleus of an atom, you can understand how difficult it is to detect these things. Now, just as ocean waves come in a variety of wavelengths, similarly, gravitational waves should come in a variety of wavelengths, of distances between the crests.
Gravity waves come not only in different heights and wavelengths, but also in various shapes, called waveforms. These waveforms arise from different types of events in space.
And in fact, by looking in detail at the waveform, one should be able to decipher the details of what the source was and what it was doing. For example, if you have two black holes that are going around each other, they spiral together, whirl real fast and coalesce to form a single black hole, you'll get a unique waveform that will jiggle back and forth faster and faster, and then you'll get a dying out jiggle. If you looked at some other kinds of gravitational waves, you may have a very different kind of a waveform. There may be a waveform that just goes bloop, and that kind of a waveform could be produced in a supernova explosion, for example. And so if one goes out with a gravity wave detector and sees the bloop waveform coming in, one infers first that, yes, that was a supernova explosion, but also with a network of several gravitational wave detectors, one can infer just where on the sky the supernova explosion occurred. And one can then go out and immediately notify by telephone observational astronomers at the large optical telescopes and say, there was a supernova explosion right in this particular region of the sky. You should go train your telescopes on it and watch for it, because you'll see the light becoming very bright there within the next several hours. The point is that the gravitational waves come out immediately, but the brightening of the light in a supernova will occur only after an hour or two later on. So there is time to notify your optical colleagues to go look. And so far as I'm concerned, that is the real meat of this business, is to turn gravitational wave detectors into a tool for astronomy, for probing the universe, and for learning the detailed behaviors of great, huge masses, black hole collisions, supernova cores, and so forth. Much understanding of how gravity waves behave and how they're produced has come from research done by my students. Regardless of where I am in the world, I still work with my students at least once a week. If I'm not in Pasadena, I talk to them one after another by speakerphone, and we discuss each student's research. Now, let's begin with you, Fernando.
Tell me what you've been doing the past week.
Teaching students how to do research follows the time-honored tradition of apprentices working hand in hand with master craftsmen. Give me brilliant and creative students, and I'll set them moving in a direction such that they do such great work that it will often eclipse my own.
In Moscow, Grishuk works with his students on the subject that most fascinates him, the gravity waves produced in the Big Bang. Like Thorne's students, Grishuks sometimes find things their professor missed. 3 of them have found a stumbling block that may hinder detection of Grishuk's cherished waves, a stumbling block Thorne thinks may be major.
Leonia and I have some disagreement about the prospects for detecting relic gravitons, gravitational waves from the Big Bang. Leonia and I agree that the best way to go after these relic gravitons is by means of gravitational wave detectors flown in space. However, as Leonia's own students, Lipunov, Postnov, and Prokhorov have shown, there is likely to be a background of waves produced by another source, binary stars, where 2 stars orbit around each other. And those waves are likely to cover up the relic gravitons that are so important to Leonia and me. The question is whether there is some region of frequencies, probably at the high frequency end, where the waves oscillate real fast, where the waves from binary stars will become much weaker and the relic gravitons will stick up above them. Leonia is quite optimistic that that'll be the case. I think it's going to be nip and tuck.
But Thorne and Grishuk agree that the most promising way to detect faint gravity waves from the Big Bang will be to build a system like LIGO in space. A system on Earth would suffer too much from vibrations in the Earth itself. A LIGO system in space would be a technological high-wire act, using laser beams that reflect along paths 6 million miles long. But a space-based LIGO lies decades in the future. It is the only type of experiment yet conceived that could probe the very earliest moments of creation, earlier than a billionth of a trillionth of a second. Theorists who seek to understand this era must unite the vastness of astronomy with the minuteness of particle physics.
Astronomy, in some sense, is a branch of physics. It's a branch of physics that deals with what we see through telescopes. And it all comes together in the basic issue of the nature of space and time.
There was some time where there was no time. There was no even notion of time. So you can go back in time and suddenly you can discover that you cannot assign any meaningful concept to the notion of time. It was so different physical universe that the very notions of time and space did not exist.
I'm trying to get into some of these deep issues, which are very far from ordinary experience, but for which we have strong hints about in our attempts to understand the origin of the universe.
This is a world where normal laws don't apply, an almost incomprehensible world that can be explored only in the mind.
Sometimes I talk about the early universe as if it hasn't happened yet, because I, like other theoretical physicists, spend much of my time behaving as though I were God, in the sense that we have our own theoretical model universes that we play with that approximate our own universe. And we think in terms of turning the universe on and watching it expand, or turning the laws of physics on and watching them develop. A holy grail for theoretical physics is to understand the creation of the universe. We have 2 great bodies of physical law, Einstein's laws of curved space and the laws of quantum mechanics. And by marrying them to each other, we hope to understand the very creation. These 2 sets of laws are like water and soil. When you mesh water with soil or with sand, you can sometimes get quicksand, which sucks you into it in a way that neither water nor soil can do. In the same way, if you merge curved space with quantum mechanics, you'll get a new set of physical laws, the laws of quantum cosmology, which govern the very beginning of the universe. The laws that determined the laws, other laws that came out of the beginning of the universe, determined the particles that came out of the beginning of the universe, determined ultimately the birth of galaxies, the solar system, and us.
Mr. Ernst Schlegel-Hofer
The few scientists who grapple with deep questions of quantum cosmology are scattered throughout the world.
British Airways desk.
In terms of quantum cosmology, my favorite field, I think that Cambridge School is the most close to my way of thinking. So for me it was always important to go to Cambridge to talk to people like Stephen Hawking, Gary Gibbons, or Malcolm Perry.
Malcolm Perry is a member of a group of theoreticians led by the well-known physicist Stephen Hawking. Grishuk has come to interact with this group.
Coordinates don't lie on the real line, but are in some sense constrained to lie on some other manifold.
To physicists, interaction has both a technical and a people meaning. Technically, interaction occurs when tiny particles collide, sometimes forming new kinds of particles.
Not of eigenstate of something like that.
On a personal level, interaction means a mental collision, one that may yield new intellectual fruit.
Negative.
You know, you started too technically. I mean, can you please repeat? So I didn't understand.
Oh. If the variables live on the whole real line.
But in science, each subfield has become so specialized that it may take 2 or 3 days, a week, for scientists to explain their work well enough for colleagues to understand. Only then can they ask meaningful questions or offer contributions.
If they live on a circle, it's actually rather hard.
Since the 17th century, Cambridge University has been a center of theoretical physics in England. Newton walked these streets, working out the basic theory of gravity, which Einstein's theory superseded 2 centuries later.
I times A, and crudely speaking, pi is the same thing as IA d by dA. Whatever theory you have to take account of these problems. If the theory is no good, well, you invent a new one. But
even though Grishuk has come to Cambridge at the invitation of Hawking's group, to interact with Hawking himself often proves difficult to coordinate.
Hello?
Hello. So hello.
Nice to
Glad to see you again. I wanted to ask you whether Stephen is available and is it possible to talk to him for a while?
He's going off to Spain on Thursday.
Just I wanted to report some of my recent work. I would like to see his face and whether he says yes or no.
Interaction is so important that the British scientists have built it into their tea time. Twice a day, everyone gathers in the interaction room for tea and theory.
So I first computed the horizon size and discovered that it's applied for perturbations smaller than the horizon size just oscillate, and perturbations which are larger than the horizon size are frozen.
Hello, Stephen.
Yes, hello.
I would like to continue this because it is exactly what I'm doing now.
Yes.
But may I ask Stephen, since I just...
Now you may want to come around here and look at what he's actually saying.
Straight is the easy way to see.
Stricken with Lou Gehrig's disease, muted by a tracheostomy, Hawking can now communicate only through a computer voice box, which he manipulates by squeezing a control instrument.
Squeezed quantum states and particle creation, and I'm now excited with this. It sounds interesting. Right. I'm really excited because, you know, now I'm thinking how to maybe even to apply to real observations. And these states must always be squeezed. Even in your process of particle creation in black hole situations, it turns out that there are 2 more squeezed states. But it is rather an exceptional case. For instance, for gravitons, I can distinguish gravitons created as a result of
Stephen is among the most inspiring people in the world. He may not be always absolutely right, but on the other hand, everything he suggests something absolutely new perspective, new way of thinking. It is very interesting that this technical difficulty in communicating with him turns out not to be so important.
There is a deep reason for it.
important thing in my work. The fact that I love it. The most important is that it gives you enjoyment and it supports you in your life. If you're observing stars, if you are thinking about universe, then some minor difficulties in your life, they are not so important.
And this is the H, and this is done in terms of the frequency of the gravity wave. The frequency response, F is the frequency of the gravity wave. And there's some symbols in this for the delay line, which, and we will talk about for the Foggy Pro as well, which are important. P, the storage time of the light.
So, in my conversation with Brzezinski, when I was in Moscow last August, he described...
Places that Grishuk and Thorne explore in their mind may seem strange and exotic. But so once were the theories of Newton and Einstein.
Interferometry for radio.
Yes.
It is radio interferometry.
Right. But the dispersion in the plasma is the limiting factor, or one of the major limiting factors. So, a couple of theories there.
As the boundaries of the universe continue to be stretched, they will open new vistas, new waves to the future.
I think that future of gravity wave astronomy is very bright, because gravitational waves, they have incredible ability to penetrate through depths of matter, space and time, to study the real nature, exploding stars, coalescing stars.
Can you imagine the relic gravitons as being like those sparks of fire coming off?
No, they're absolutely isotropic, so they're not localized.
Some of those are isotropic.
Locally, but you shouldn't.
I suppose that to some people, dreams of gravitational waves look like medieval theologians musing over how many angels can dance on the head of a pin. But I'm confident those gravitational waves really exist, that they bathe the Earth, that they're passing through me right now. And I am confident that one day the LIGO detector will be shaken by a gravitational wave in a manner we never expected, that its shaking will bring to us a picture of a totally new kind of object, something so new that it creates a revolution in our understanding of the universe.
Next Monday night, the Astronomers charts the birth, life, and death of a star. Be sure to join us for the Astronomers next Monday night. Now stay tuned for The Shape of the World, next on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Video cassettes of The Astronomers and a complete set of educational materials are available from PBS Video. To order, call 1-800-222-5796 or write to the address on the screen.
Life is going down the tubes.
You're a sneaky, crude, offensive man.
Until she meets up with a very available Cary Grant.
I don't know why I left. I must have gotten panicky.
And the rest is John Aston Cary Grant and Doris Day star in the 1962 comedy classic, That Touch of Mink.
Saturday night at 10, following Operation Petticoat on TV 12. You're tuned to TV 12 WHYY.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
All across the universe, throughout billions of galaxies, stars live out their lives as others are born. Inside huge dark clouds of gas, a star suddenly ignites. But why?
We're trying to understand how stars form. The problem is so vast that nobody has a single answer.
Yet our own sun has given astronomers clues to the mysteries of the life of stars.
We think of the stars as lasting forever, but they don't. They may last for enormous lengths of time compared to human existence, but in the end, they all die.
In 1987, in a neighboring galaxy, a seemingly average star experienced a violent death, blowing up as a supernova. In Australia, giant telescopes are aimed at this rare explosion.
We're looking at a supernova now more than 3 years old. That's never been done before. We don't know what we might find.
We owe our lives to our local star, but we are also connected to the violent demise of distant stars.
It really is true that the whole of the Earth and everybody on it is just a product of stardust.
Stardust, the lives and times of a billion stars. Next, on The Astronomers. In a tunnel beneath the nation's capital, a commuter train carries astronomer Benjamin Peary to work. In our urban society, there are few reminders of the natural world around us. Peary remembers a childhood in a small Minnesota town when the sky was always blue and the stars shone brightly every night. Today, through the glare of city lights, we often cannot see the stars above. Now a professor of physics and astronomy at Howard University, Peary recalls his first curiosity about the stars when he was a student.
As an undergraduate at the University of Minnesota, well, I had often looked up at the stars and wondered, what in the world might they be? Astronomy was not a large thing. The public had not discovered astronomy. Even physicists hadn't discovered astronomy. But when I was a senior, I remember I used to stand out in the frozen Minnesota night and look at those stars and grow more and more irked and embarrassed. As a senior and physics major and not know what these things were overhead. I decided, on the basis of all this consuming fascination that I was developing for those icy blue lights up there, I discovered that there was something called astrophysics, and I decided that just had to be for me. Not many students have seen the stars, have really seen anything but a few bright lights out there. So that's the sadness that arises. The other thing that arises is that they're astonished, and they wonder why stars have different colors and all that. What are they? How far are they? Why are some bright, some faint? What are they made of? Why do they shine? And with a little prodding, we began to get just a flood of questions in order just to account for that amount of energy.
The thermostat, so to speak, helps control the rate of energy flowing out of the sun. Or does it not?
Yes,
okay,
it does.
It hasn't, a change, that flexibility in temperature hasn't occurred in centuries.
Not dramatically. Okay. Now, that's the second point I want to make in just a moment.
At the nearby U.S. Naval Observatory, Peary introduces his students to the world of astronomy.
I can see how early astronomers got caught up in the poetry of the moment and the geocentric idea, and the heavenly bodies were perfect and circular motion. I can see how they got caught up into that, because when you look at the sky, if you lean way back and you just look at it, it's like this black covering with these different sparkly, designy, colorful lights, and they twinkle and they seem so perfect and so unmoving. It's kind of like God made it just for, you know, the earth, just to engulf the earth, you know. So it is an interesting class.
Lots and lots of history there.
For Benjamin Peary, the telescope has been both an inspiration and a tool for discovery. As an educator, Peary hopes to share with others what he has witnessed personally. As a professional astronomer, there was a time when Peary enjoyed a privileged view of the lives and drama of stars.
A brighter star and a fainter star, and that's the way it used to be.
The stars we see in the night sky are only a handful of all that populate our galaxy, the Milky Way. Though stars appear unchanging, like humans, they are born, they live, and they die. Within dark clouds in interstellar space, new stars are born. How this happens still has much mystery for astronomers. Most stars die quietly, gently fading. But some end their lives in a vast explosion. Their ashes, rich with newly formed chemical elements, mingle with interstellar gas to become the raw material of new stars. Our galaxy is just one galaxy among billions. The sun, our star, moves in the outer suburbs of the galaxy, in the curl of one of its spiral arms. As the galaxy rotates, it takes the sun 240 million years to make one orbit around the galactic center. And the sun, in its life, will make many orbits. The brightest stars in the spiral arms lead briefer lives. As the galaxy makes a single turn, there is time for many generations of these stars to live and die. We know that stars are born, but how? We know that stars explode, but why? We seek the answers because stars, planets, even our own bodies, are made from stardust.
When I go out in the night sky, in a place where you can really see the Milky Way, I rarely think of it as a scientist. I look at the Milky Way, it's the same impression that everybody else gets, and that's just, wow!
A father-son fishing trip on Chesapeake Bay is an opportunity for astronomer Leo Blitz to share his excitement and love of the stars. It is an enthusiasm that exceeds the bounds of science. For nearly a decade, Blitz has sought to unlock the secrets of the Milky Way. But the best-kept secret of all still eludes him. That is the mystery of how stars are born from the near emptiness of interstellar space.
We understand the life cycle of stars pretty well, except for that part which occurs when stars are born. When we look, even through ordinary light telescopes, at the space between the stars, it looks empty, completely empty. And the emptiness is really far from the truth. The space between the stars filled with matter, with gas, that stuff is really important because that stuff ultimately gets collected together by processes that we don't fully understand to form new stars like the sun.
To find a star like our sun at the very early stages of formation would be a significant advance in astronomy. For Leo Blitz, it would be the culmination of a decade of research. From the College Park campus of the University of Maryland, Blitz directs a major effort to solve the mystery of star formation. For him, it is a childhood dream come true.
I was one of those kids who, when they were in first grade and the teacher asked them what they wanted to do, I said I wanted to be an astronomer. It was a simple fascination with space travel, rocketry, the solar system. When I became an adult, I became a kid again. What greater enjoyment can you get than to do the things you wanted to do as a kid and actually get paid for it?
In the basement of the astronomy department, a dozen scientists recruited by Blitz seek to understand how stars form. He has nicknamed them the group.
Oh, Zhong-Hee. Were you able to get any? What we've done is put together a group that has roughly 12 people. Everybody's involved in the process and getting involved in questions of star formation and in the research that we do. The deadline for proposals...
When Blitz arrived at the University of Maryland in 1981, he was the only person in the astronomy department working on star formation. As the inquiry accelerated, the team grew, and the need for communication became more critical.
I've got 3 doors to my office, and I expect people to be able to come in and use any one of them. We have a seminar every week. We get together every day for lunch. We're always talking science, and we're doing it not because we have to, but because we want to. That's what we think about.
Is this going into the proposal?
No, this is actually for the paper.
Okay, so make sure that that gets done.
Okay, sure.
Do you have Hat Creek? Can you bring up?
All right, can you go back?
We got to see what's going on at the site.
From a computer terminal in Maryland, Blitz and his team can direct by remote control radio telescope receivers across the continent at Hat Creek in Northern California. Signals received by the Hat Creek radio telescope could lift the veil of mystery surrounding the birth of stars. The light from stars can be detected by optical telescopes, but stars that are forming do not yet produce light. Instead, they emit radio waves, so a radio telescope can see into star-forming regions. A trio of radio dishes forms a single powerful instrument that Blitz uses in his search. The telescope can maintain a 24-hour-a-day vigil, scanning the star-forming regions of the Milky Way.
This is the Milky Way. This is our home galaxy. This is where we live. It's where we're always going to be stuck because we can't ever get out no matter what else happens. This particular mosaic is, I think, the best one that's ever been done of the entire Milky Way. What we have to do is imagine that we are the sun. We're standing on the Earth around the sun, and the Milky Way is all around us. And the region of the galactic center is right about here. The center is hidden by this dust, these dark regions, which were once thought, in fact, to be holes in the stars. And it's these dark spots that contain molecules and dust. And the stars that are forming inside of them. They're completely invisible to optical telescopes. In a few places, we can see that some of the stars are beginning to break out of this dark material. And that's just what's happening here. These objects are just now emerging from these cocoons in which these things have formed. Before I started graduate school, I was in industry, and My boss had, at the time when I told him I was going to graduate school, he said, what a life, you know, all you have to do is just sit around and you think. And I discovered once I became a professor myself that was far from the truth. Typical days are 12, 14-hour days. There's teaching, there's writing, there's research. For me, there's running the group. And the most important thing of all is the time that I spend with my son. Hi, puppy. Come on.
Oh, you got a haircut.
Yeah. Throw this in the back. We get to do this and they stay wet. Brian is with me half of the time, and it makes for a very full life. I try to cut out that amount of time that's left for purposeless things, although everybody still needs just to be able to goof off. The demands on my time recently have gone up. It seems to me that I need more than 24 hours a day, and yet there are none. And unfortunately, in the last year and a half, I've played no squash, and that's something for which I have a great passion. But the one thing I can't give up, I won't give up, is that time that I spend with my son. There's nothing that's more important to me than that.
While Blitz juggles life as father, scientist, and academic, he is personally driven by the desire to know how we fit into the universal scheme of things.
We look for the way in which stars form for several reasons. One is a quest for our origins. We live here on the Earth, we're a planet around the sun. We know from geological evidence that we've been around for 4.5 billion years. How did we get here?
To Blitz, the question of how we came to be, how a star like our sun was formed, drives the research effort forward. Each week, his star formation team meets to assess the latest observational data on the star-forming regions of the galaxy.
The most massive clumps here are these. They're all in the midplane of the cloud. Some of them have stars forming in them.
Team members have been handpicked by Blitz from the United States and 6 foreign countries. Among the International Assembly is a postdoctoral fellow from Holland, Eugène de Huys.
At higher frequency.
De Huys and Blitz are planning an observing run at the Hat Creek Radio Telescope Observatory. They hope to detect a star before it ignites, a protostar.
That's right. So then,
in the coldest, darkest parts of the galaxy, a protostar is born from clouds of hydrogen gas and other elements. Radio waves reveal how the gas moves within the cloud. Mapping the radio waves produces a picture. Blitz and de Huys hope to discover a region where the gas is condensing to form the core of a young protostar.
One of the reasons that the existence of a protostar is so hard to really prove and so hard to find a protostar is that it's not really putting out its own light. For instance, like a star. I mean, a star is obvious, right? You can see it. So that's one of the reasons that finding a protostar is very difficult. Although if you could come up with a way to do it, that would really be extremely interesting, and that would be really a fantastic advancement in the study of star formation.
it's like trying to find buried treasure at the bottom of the ocean. What happens is that the blackness of the ocean just soaks up all the light. You might try to shine light from the surface and to try to illuminate something like the Titanic at the bottom of the ocean, but you can't see it because the light is all absorbed by the intervening material. And so what we want to do is to go up to Hat Creek and look in detail at one of the regions where we have some evidence from other observations that we have condensations that look as if they may be forming stars.
At the remote Hat Creek outpost, Blitz and de Huys will spend a week investigating a star-forming region called the Rosette Nebula.
The other source is 250. It's it's about 1.5 times as
Oh, it's 17,
weak.
right,
Yeah.
okay.
For Blitz and DeHoyce, Hat Creek is a listening post, their stepladder to the stars.
2.1 minutes is what it gives us the error if it
Okay,
can't get a
there's
fit.
Yeah, there's something wrong.
So let's do this again and do it with a longer integration time so that we get more signal.
Let's do 20.
Okay, now we're fine.
That's nice.
We
So
can-
we'll let this one finish.
Because star formation takes thousands of years to occur, Blitz and DeHoyce cannot witness the actual event of stellar birth. But radio signals can provide a snapshot of the process.
Right now, what we are looking at is the radiation that comes from individual molecules. We look particularly at molecules such as carbon monoxide, carbon monosulfide, CS, HCO+. We can see the motions of that material. And in some sense, what we're really doing is looking at the cold part of the universe. When stars form, they form out of very, very cold gas.
The Rosette Nebula is a bright region within a larger, dark molecular cloud. In the glowing heart of the rosette, hot, young stars light up the surrounding gas and dust. It has taken about 10,000 years for these new stars to blaze forth from their gaseous cocoons. For Blitz and DeHoyce, the search is not in the glowing and brilliant area of the rosette. It is in the surrounding dark regions of the larger molecular cloud. Blitz can imagine what takes place within that darkness.
If we were traveling through space and we could travel very fast, we would notice as we got close that this cloud of material breaks up into little pieces. And as you move into one of these things, what you might notice is that suddenly it becomes very bright because the star has begun to burn its nuclear fuel and very likely would have jets of material that are coming out, which are almost surely a necessary consequence of the star formation process. On occasion, we make discoveries, but really what we do is we create the universe in some way. And what I mean by that is we make observations. We see things here at the telescope, for example. We rarely look at things that have not been seen before, but we try to create order and understanding from what it is that we see. The entire idea that stars form at all is only about 200 years old. How stars generate their energy, we now know comes from nuclear fusion, and that process was elucidated by Hans Bethe in 1939. It's the work that he won the Nobel Prize for, quite fittingly.
I was born on July 2, 1906, in Strasbourg, in Alsace, which was then German and later became French.
Cornell University in Ithaca, New York, is now home for the man who discovered how stars shine. It was here over 50 years ago that Hans Bethe calculated in detail how stars produce energy. His interest in stars arose from a wider curiosity about how the universe works.
I want to find out how the world is made. What is it made of? What holds it together? What makes it operate the way it does?
Growing up during the first 2 decades of this century in Frankfurt, Germany, Hans Bethe showed an early brilliance in mathematics and physics. He began his career as a lecturer in the German university system. Then the Nazis came to power. When he learned that his Jewish ancestry disqualified him from teaching, Bethe emigrated to England and then to the United States. He arrived in February 1935 to become an assistant professor at Cornell University. Bethe took to Cornell immediately.
I became a member of a very friendly group of physicists here at the physics department. I found it most satisfactory. I loved them, they loved me, so I stayed.
In 1938, Bethe attended a conference of physicists in Washington, D.C. The meeting had a profound effect on his life and work.
They thought it would be nice to discuss the nuclear reactions in stars, how the energy in stars was generated. Nobody knows really what nuclear reactions take place and what makes the energy. And that was something which I thought I could work on and might be able to solve.
Just 6 weeks of concentrated effort led Bethe to the answer. Bethe knew that the sun shines by nuclear fusion. Hydrogen, the basic ingredient of all stars, is fused into more complex elements. In this process, matter is changed into energy, according to Einstein's famous equation, E equals mc squared. Bethe's achievement was to determine the exact sequence of nuclear reactions that occur and the precise rate of energy production. At the center of the sun, every second, 4 million tons of matter are converted into energy. So massive is the sun that it takes millions of years for this energy to reach the surface, which rages at a temperature of 10,000 degrees Fahrenheit.
In this reaction, an enormous amount of energy is set free. Enough, certainly, to keep the sun and other stars going for millions and millions of years. In the case of the sun, for instance, it will last for a total of about 10 billion years. Once, when I gave a talk like this, one of the people in the audience asked me, did I say million or billion? And I said billion. Oh, he said, I am relieved.
In the summer of 1938, Bethe published his discovery of how stars shine in a journal that offered a prize for the best paper. He used most of his $500 award to help his mother emigrate from Nazi Germany. It was not the only prize Bethe would win for the work he did that year. He was awarded the Nobel Prize for Physics in 1967. Soon after his discovery of how stars produce energy, Bethe and many other scientists saw that the conversion of mass into energy had awesome possibilities for warfare. Nuclear weapons were the result. In 1945, the atomic bomb ended the war in the Pacific. Soon afterward, the precarious world of the Cold War produced the most powerful weapon in human history, a device which uses fusion processes almost identical to those in stars, the hydrogen bomb.
5, 4, 3, 2, 1.
On February 23, 1987, an explosion was detected that was 1,000 trillion times more powerful than the hydrogen bomb. It was a supernova. A massive star had undergone a dramatic death. The exploding star suddenly appeared in the Large Magellanic Cloud, a companion galaxy to the Milky Way. It was the brightest supernova seen from Earth in 4 centuries. Because of its location, the supernova could best be seen from the southern hemisphere. The seaport metropolis of Sydney, Australia, became a gateway for astronomers from around the world who hoped to gain new knowledge about the death of a star. At the Anglo-Australian Observatory, researchers have followed the supernova ever since. The news of its first appearance will never be forgotten.
It was something that blew up 170,000 years ago, and the light has just made it to us.
It completely stopped dead all the other research programs that I was working on.
Peter was running up and down the corridors of Imperial College, knocking on people's doors, saying they've discovered neutrinos.
That was certainly nearly as exciting as the supernova itself.
Yeah,
yes,
I think
yes.
it's absolutely amazing.
I think everybody who was involved remembers what they were doing, just like when Kennedy was assassinated. You remember what you were doing when you heard about it. And there was I happily down in that building over there, working on data, and somebody came along, a colleague came and sat down and said, "Have you heard about the supernova in the large cloud?" I heard about supernova. I was busy typing away. Suddenly started thinking, just a minute, supernova in the Large Magellanic Cloud. Yeah, that's going to be visible to the naked eye. That's closer than any supernova we've seen for 400 years.
The supernova was destined to change the life of Mike Doppiter. Doppiter is an astronomer at Mount Stromlo Observatory in the capital city of Canberra. For 15 years, Australia has been home for Czech-born Doppiter, his French wife Patricia, and their son Igor.
Supernova 1987A is a real keystone for understanding stellar evolution. And this is really great because now we can put handles on lots of parameters of stellar evolution theory, which up to now have just been in the realm of speculation.
Like other astronomers, Doppiter remembers well the moment he received the news that a supernova had exploded and was actually visible in the sky above Australia.
Well, I was sitting down at the dining room table there, and I picked up the morning newspaper. And there on probably, I think it was page 3 or 4, because it wasn't considered very important, news, supernova discovered in Large Magellanic Cloud. I thought, but man, that can't be true, for God's sake. And so I went and rushed up to Stromlo and discovered that they'd actually heard about it the afternoon beforehand, but no one had bothered to tell me because I was working at home.
Well, Mike comes back home and he says, "Oh, I've discovered something tremendous," and I hear it all the time, so I've become very blasé about it. So when he talked about the supernova, for me it was just one of his discoveries and nothing more.
Oh, it made a complete hash of my life. I was there happily going on doing the research that I was doing, and then all of a sudden this thing goes off, and I just simply had to go and start all over. First of all, I had to learn about what supernova were all about, because although I'd been working on supernova remnants, I never kind of dreamed that this kind of an event would actually happen.
Observing the supernova became a way of life. The flight to a remote telescope facility in Siding Springs, several hundred miles away, has become Doppiter's regular commuter run.
We're flying up from Canberra to Coonabarabran, which is about 400 kilometers north, and it's sort of on the edge of the Great Australian Dry, where you get much clearer skies, much better conditions for observing, and it's a very, very dark sight. And so we've put all our largest telescopes up at Siding Springs, and I shall be observing the supernova because now it's 3 years on since the supernova went off, and the supernova's become very, very dim, and we can only observe it using the largest telescope. So I'll be using the 2.3 New Technology telescope. In addition, there is the 3.8-meter telescope, which is operated as a joint project between Britain and Australia, the Anglo-Australian telescope, and that will be used for infrared work. 3 years on now, and I'm hoping to be able to observe it up to about 5 years, 10 years. Well, I'll just keep on observing it and see what happens.
David. How are you going?
The frontier settlement of Coonabarabran is the starting point for the journey to the observatory complex through the rugged Warrumbungle National Park.
If it wasn't for supernova explosions going on through the 10 billion years that our galaxy has been in existence, we wouldn't have the elements that we need to build planets, and we wouldn't have the elements we need to build life. I mean, it really is true that the whole of the Earth and everybody on it is just a product of stardust.
Siding Spring Mountain is the major astronomical research center in Australia. It draws scientists from around the world. Many come to observe supernova 1987A, named for the year in which it appeared. Dapita and others want to know how, within the cosmic furnace of an exploding star, the rare heavy elements of the universe are forged. Without supernova explosions, there would be no Earth, no other planets, no life.
Well, supernova 1987A was really neat in that it chose to go up in the Large Magellanic Cloud, the nearest galaxy to our own. We know exactly how far away it is. And we have a kind of view right up out of the galactic plane, so we can see the thing very clearly.
Well, here's the telescope. We're tipped over looking at the Large Magellanic Cloud, and the light is coming from the Magellanic Cloud, its journey of 160,000 years and the extra 3 since it went off, to land in the mirror and be reflected and to be gathered in by our instruments. This telescope has been designed for maximum efficiency, plus the fact that the whole thing is under computer control, so that we can simply press a single button in the control room, just one single observer, and the telescope will come and track to the object.
The great thing about observing is that sometimes, you know, it's routine, it goes on night after night, and then suddenly you get something which is completely out of the ordinary, and then the adrenaline flows. And even if you haven't made a discovery, just the joy of the hunt at that point really fires you up and keeps you going for a few more hours. The supernova, I've been living with it now for 3 years. I mean, it's almost as if we were married. You get to know all the little bumps and wrinkles of the spectrum, and you see it gradually changing and getting old, falling apart, and eventually will become too faint and diffuse to observe. What I'm trying to do is monitor it over the years and understand the way it evolves. It's completely different from what it used to be even a year ago, and it's changing continuously. Ah, and here it comes. We've got neon 5, neon 3, there's the hydrogen lines. This is magnesium. This is one of the elements that makes rocks. This is the iron that was originally the radioactive cobalt. I can tell from this it's actually way down in the core of the supernova. This is really what I'm trying to get to. I'm trying to understand how the different layers of chemicals are produced in this supernova.
In the spectrum of the supernova, Dapita can read messages that tell of the star's short life and violent death. Most stars burn steadily for billions of years. Ultimately, they use up their nuclear fuel and quietly fade away. A massive star, one with 20 times the material in our sun, burns at a frantic rate. When its hydrogen fuel is almost exhausted, the burning accelerates. The star grows larger. Deep inside, nuclear fusion continues. At its core, the star continues to create and burn heavier elements, such as oxygen and silicon. Finally, at the very center, the star forms iron. But iron cannot serve as nuclear fuel, so energy production stops. And when the nuclear furnace shuts down, the core of the star collapses, setting off a gigantic explosion. A supernova radiates with the energy of 10 billion suns. All the elements the star has made, including those needed to make up living creatures, mix into the interstellar medium, enriching the gases and planting the seeds for new stars, planets, and people. While Dopita searches for stellar ashes created in the furnace of the supernova, others are seeking a far more exotic byproduct of the exploding star, an object called a pulsar. The hunt for a pulsar in the supernova remnant has started an international race among astronomers. One of the searchers is Australia's Richard Manchester.
I've been really working on pulsars for pretty well the whole time that they've been known about. So it's a challenge to find these things, and we've been fairly successful at it. The searches that I've been involved in have found about half the known pulsars. It's about 200 or 250 altogether, so it's been good.
Even for a seasoned pulsar hunter, there is no guarantee of success, because not every supernova event produces a pulsar. A pulsar forms from the core of a dying star. As the supernova explodes outward, the star's core is crushed by gravity and collapses inward to form a spinning, super-dense object called a neutron star.
Neutron star is really an incredible object. It has the same mass as the sun, but it has a size of only about 20 miles. So you've got all the material of the sun compressed into a thing only about 20 miles across. Just to illustrate how dense that is, if you could bring a sugar cube of neutron star material to the Earth, it would weigh 100 million tons.
A neutron star can become a pulsar as it spins rapidly, generating radio signals in its strong magnetic field. Radiation beams sweeping through space like a lighthouse may be picked up by radio telescopes if the beams sweep past the Earth. Since the supernova first appeared, Manchester has used the 280-foot Parkes radio telescope to search for its pulsar.
Being a pulsar person, I thought, there's got to be a pulsar in this thing, let's go and find it. So observed the supernova, which was very bright then, looking for a pulsar in it. It would have been really fantastic to find one, even though the probability of success at that time was pretty minimal, but had it come off, it would have been a world beater. It didn't, of course, and I'm still looking for the pulsar.
Before he trains the dish on supernova 1987A, Manchester fine-tunes his instruments on the well-known Vela pulsar.
I will type in
The Vela is a young pulsar, a mere 100,000 years old.
one. Out the tape. I think we've got everything set up now, so we have to go and look at a strong pulsar and see if it comes in okay. Beginning to go. And Levels. Okay, well, let's see if we can get it on the audio. There it is. Dealer pulsar is in a supernova remnant. The pulsar in SN 1987A might sound like this if we were able to pick it up. We need to go switch on the control system. This is going to take a while. Okay.
What's the reading?
5 and 3. We're going on to SN 1987A to see if we can find the pulsar there. We've looked many times before, so the chances of finding it this time are not high, but it'd be so exciting to find it that we keep on looking.
Any pulses from 1987A should be weak and therefore are likely to be buried in a sea of noise. It will take Manchester months to analyze the data he collects tonight and to sift out the obscuring noise. Even if a pulsar does exist in 1987A, it may never be seen. Its beam could sweep across space but miss the Earth entirely. But if the beam does not pass our line of sight, a pulsar could reveal its presence indirectly. Gas surrounding the neutron star would be heated by the rotating beam. So astronomers may be able to detect a pulsar from the glow of the surrounding gas. The largest telescope on Siding Spring Mountain is aimed at 1987A. David Allen of the Anglo-Australian Observatory is trying to detect the pulsar by the indirect method. He uses an infrared heat detector on the optical telescope.
What's happening to the supernova is fading. But if there is a pulsar there, that pulsar should stop it fading, should hold the energy, and in fact cause the gas to appear hotter. And since we're able to monitor the physical state of the gas, we're looking for evidence that the gas is getting hotter as the rest fades away.
You have to have one person who is self-sacrificing and watches it to tell you when to say
Tonight, Allen and his team will look at the heat radiating from the supernova remnant. Energy from a pulsar would be heating the gas around it.
The temperature of this liquid nitrogen is about minus 330 Fahrenheit, which is even cold by the standards of places I've visited in the US, Alaska.
In order to measure the heat from a pulsar, Allen must make sure that the detector on the telescope remains cool. Heat from the detector itself could overwhelm faint signals from distant sources. Liquid nitrogen provides the coolant.
Now, the actual infrared detectors, and when we pour the liquid in, the detector is inside, attached to the metal that this liquid cools. And so it itself is cold. Right, this liquid nitrogen is actually cold enough that it freezes things like banana skins solid. As long as you're out of the way, you can get rid of it.
What do you want to do here? You want to...
I want to do an arc in a minute. That's come out the same there, right? Okay, let's go to the standard. So we haven't lost any data.
Well, you're running at 40 milliseconds?
Yes, gain 100 on the arc.
40 milliseconds.
That was fine. Okay, I'm going to put the arc on, Steve, so... TV down.
As data is received, the supernova reveals a new, unexpected story.
You happy? Running.
We thought when we started we maybe would find some evidence of a neutron star, pulsar. So far, that's not working out. It's getting terribly hard to make these sorts of observations. We just can't say anything conclusive. But instead, we've bumped into something by chance. I mean, this sort of happens, you know, you can't predict science. What we've bumped into, maybe we should have thought about, but we're able to detect some hydrogen, commonest gas in the universe, that hasn't previously been seen associated with this supernova.
The hydrogen that Alan has discovered is gas blown from the star before it exploded, revealing conditions within the star before it went supernova.
You never know when a star is going to become a supernova. They don't jump up and down and wave a flag and say, hey, I'm going to explode in 100 years. Right? So you never have a chance to go along and study a star in the expectation it's going to go bang tomorrow. The only way you can do it is to work your way back, having seen it go off, is to try and work out what was there beforehand.
By understanding what happened to 1987A, astronomers hope to determine which stars in our own galaxy have the potential to explode.
We know from supernova 1987A that stars that we thought previously were not really candidates for supernova explosion could go supernova quite unexpectedly. So we're now looking for objects which are like supernova 1987A. In our own galaxy, there is a star, famous star Eta Carinae, which has varied in brightness enormously and blown off shells of gas. So this fellow's saying, look, I'm unstable in my outer layers. The real question is it unstable in the core?
Eta Carinae is the most luminous star in the Milky Way. It radiates as much energy as several million suns. Astronomers predict it will end its life in a supernova explosion, sometime within the next few thousand years. Supernova 1987A is helping to identify less obvious candidates, stars that may meet a violent end far sooner.
I think that the great thing about supernova 1987A is it teaches a lot of things. It was very, very exciting for a while there because you didn't know what was going on and you were hunting. It was the joy of the hunt. And then you found things quite unexpectedly that you didn't know existed. And that's the great thing about research. It's the hunt that's the thing.
In a case like the supernova, you know, had we found something, it would have been fantastic. The probability of actually succeeding was very low, but even so, the return, if we'd succeeded, would, you know, really would have been worth it. So even though the theoretical models may say, you know, there's no chance, I'll have a go. It's just on the off chance that they're wrong.
The supernova is a terribly important event for us. We wouldn't exist without supernovas, because in the early universe, only two elements are made, hydrogen and helium. And all the other elements must be made in supernovas.
I suppose one of the amazing things when you sit in a place like this and look around is to think that everything here, the rock, the trees, me, really came out of supernovae. A supernova is the only way we know to generate all of these complicated elements, the heavy elements that are needed to make a planet, a tree, a person. So that we're all children of the stars. These are supernovae that erupted before the sun was formed, more than 5 billion years ago. And they're debris that you and I, the mountains, are made of.
We think of the stars as lasting forever, but they don't. They may last for enormous lengths of time compared to human existence, but in the end, they all die. They must use up their nuclear fuel and end their lives. And the sun is no exception.
The sun is probably going to go with a whimper rather than a bang. We're about halfway through the life of the sun. We'll wait about 4.5 billion years more before the sun begins to show its signs of old age, and the sun begins to heat itself up in the center so greatly that the radiation simply can't get out fast enough. And the result is that the outer region of the sun, as well as the core, but primarily that outer zone where so much of the energy is trapped, begins to expand.
As the sun expands, it will become a red giant, enveloping the inner planets. Our seas will evaporate, and life on Earth will be consumed by the sun's outer heat. The star that gave our planet life will take it away. But as one small light is extinguished in a galaxy of billions, new stars will blaze in the darkness. Newborn suns of the Milky Way contain the ashes of stars that have died. What began as stardust gave birth to life. What else the universe may hold is the stuff of dreams.
Tomorrow night, Nature examines the challenges to preserve the dramatic mountain landscape of Glacier National Park. That's Nature tomorrow night at 9. Now stay tuned for a Bill Moyers special, Beyond Hate, next on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Video cassettes of The Astronomers and a complete set of educational materials are available from PBS Video. To order, call 1-800-22...
1891 Mercury Tracer LTS. From the Lincoln Mercury dealers of the Delaware Valley to you as this year's Jubilee Grand Prize winner. Enter today.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
In our lifetime, we have begun the journey to fantastic worlds. Worlds that for centuries could only be imagined. An aging explorer approaches its final encounter, while the world looks on. The first close-up images from Neptune. After many triumphs and discoveries, what will be the next frontier? For planetary astronomers, the next goal is finding planets around stars other than our sun.
What we'd really like to do is find out if there's other planetary systems out there, with planets like Jupiter, or even like the Earth circling around another parent star.
Astronomers now think they've found evidence of planets around other stars. Their search is driven by the oldest of questions. Are we alone in the universe?
We're beginning to believe that there was nothing really extraordinary in the events that led to the evolution of human beings. We are now at a threshold. It's just a matter of the willingness to go out into space and to examine the nearby stars and see if there are worlds there.
From a control room in California to the Andes Mountains in Chile, prospecting for planets. Next on The Astronomers. There's a road that cuts across a desolate stretch of central Chile. For some travelers, it leads to vistas beyond this Earth. It is the road taken by American astronomers Brad Smith of the University of Arizona and Rich Terrell of Caltech's Jet Propulsion Laboratory.
We've ever seen. We get to characterize it.
They come in search of other worlds, planets around distant stars. For 12 years, they have shared a friendship, deepened by frequent trips to this remote and barren land.
Yeah. Buy some cheese. Goat cheese. You want to ask him how much?
¿Cuánto es?
500.
500. It's 1,000.
1,000?
No, that's 5. What is it? 500.
Why don't we give him 1,000 anyway? It's okay. Gracias.
For Smith and Terrell, the tiring days of travel are more than balanced by the chance to observe the southern skies.
An observing run overall is an exciting experience. You know what you want to do. You come down here and hope that the weather will cooperate. You're excited about the science you're going to get.
There's a tremendous amount of satisfaction in discovering something new. You come out here for a purpose. You've asked a scientific question. And that scientific question usually relates to a bigger puzzle, the meaning of things, where we relate to the universe, how we came to be.
Among the billions of stars in the universe, is ours the only one to harbor planets? This is the driving question for Smith and Terrell. In the foothills of the Andes Mountains, they follow a road to the Carnegie Institution's Las Campanas Observatory. Smith and Terrell bring specially designed equipment to attach to the telescope. Their device will reduce the star's glare to help search for planets that may orbit around it.
Eyepiece, periscope that allows us to look up through the eyepiece, one of the lens systems. Spare shutter in case we have a problem with that. Miscellaneous boxes of tools.
Ever since I was a little kid, I was curious about science. I just lived and breathed and read all I could about science. First time, my parents told me this first time I got hold of a screwdriver, I disassembled every doorknob in my house. I wanted to find out the way things work.
I guess my interest in astronomy began when I was about 9 years old. My grandmother gave me a book about the stars. I would go out at night with a piece of cardboard and a pencil and began drawing them. I soon found that was a pretty big job.
Okay, we're ready for another exposure.
Okay. Yeah, I've got it pretty well lined now. The periscope is out. The dark slide is open. This is the wide filter, 13 arc-second mask, and you go ahead and expose now.
Exposing.
Smith and Terrell's search for extrasolar planets grows naturally from years of pioneering work exploring our own solar system. During the last 30 years, automated space probes have given us dramatic close-ups of the sun's family of planets. They have permanently changed humanity's view of its own cosmic neighborhood. The crowning triumph of these explorations has been the Voyager mission to the outer planets, directed from NASA's Jet Propulsion Laboratory in Pasadena, California. In Building 264 on the 3rd floor, the imaging science team led by Brad Smith receives signals from Voyager, telling of planetary worlds billions of miles away.
I think I just better. I've been with Voyager since 1972, and about a third of our team has been with us right from the very beginning. That's 17 years now, and it'll be about 18 years before we finish our analysis. That's a long time to work on a project.
Rich Terrell became an astronomer a year after Voyager began the epic journey that exceeded all expectations.
The spacecraft was launched in '77, which makes it about 12 years old right now. And I don't know if spacecraft age like dogs do or whatever, but the spacecraft has encountered its problems. It's deaf in one ear, essentially, one of the receivers. It's tone deaf in the other ear. It's got an arthritic scan platform. It's hung up on us several times. It's got memory lapses. It's got other, the kinds of things you can associate with degradation, with age. But nevertheless, it's got a personality, and it's also got a brain.
Voyager has traveled 5 billion miles, giving us an armchair tour of worlds never before seen. The one-ton spacecraft has radioed back tens of thousands of pictures and a wealth of data, information that will keep scientists around the world busy for decades. At JPL, preparations begin for Voyager's final planetary encounter. Ed Stone, chief project scientist, coordinates 200 researchers involved in this detailed survey of the outer planets.
Voyager really has, I think, surveyed the outer solar system and really shown us what literally dozens of new worlds look like. And one of the interesting things I think that we've discovered is they're very similar worlds in very fundamental ways, but they're also significantly different. Each one has an identity because of its particular origin, or more importantly, perhaps, because of a different evolution that it's undergone since its formation. The inner planets are small, rocky worlds which form near the sun where only rocky material was solid. Jupiter, Saturn, Uranus, and Neptune are giant gaseous planets formed in the outer solar system where there's lots of water, which is frozen, and therefore a lot of solid material to make giant planets, which then could accumulate vast amounts of hydrogen and helium to become the large planets they are.
Encounter after encounter, as Voyager reached each new planet, the mission scientists have reassembled at JPL. Brad Smith's imaging team has had to provide on-the-spot interpretations of pictures from each new alien world.
Yeah. The Mars polar cap, and this is what it looks up close.
Yeah, okay, all right.
A little teaser.
First of all, Voyager has been just a series of surprises. And that in itself isn't surprising because this outer part of our solar system is what we knew least about from the Earth. Each planet, as it was further and further away, was less and less known to those of us who tried to observe these things from the ground.
But I think the first encounter with Jupiter really shocked a lot of people. It shocked the press because I think it was more colorful, more visual than anybody expected. And it shocked scientists because it was more unusual.
The atmosphere is variegated, almost psychedelic in its color. The surprise was the dynamics, the activity of this atmosphere, the way in which features interacted with other features in ways that we just never would have guessed.
I Gaia was perhaps the biggest shock, and maybe the biggest shock of the entire mission. Here's a moon around Jupiter, relatively small. We didn't really expect very much from it. Here's a planet, a world, where the geology changes on the time scale of human lives. While you're looking at the geology, it changes. If you lived there, you wouldn't get a weather report. There's no atmosphere, but you'd get a geology report. You know, mountain building to the east and floodplains to the west. The place is very, very dynamic. Here's a world that almost goes beyond the imaginations of science fiction authors, and it's a real place. It's in our backyard, orbiting Jupiter. The same thing was true at Saturn. There, the big showstopper was the rings. No one expected the kind of detail that we saw in the rings, and also the dynamics.
The rings, we thought we knew it all. We thought we understood them. We actually didn't expend that many images on the rings. So instead of seeing a few features that we had expected, the rings broke down to literally thousands of tiny ringlets. I guess at Uranus, the real singer was Miranda. The smallest of the known Uranian satellites. We were looking at it closely only because we had to go close to it to get on out to Neptune. What a bizarre object that had all different kinds of geologies, like samples from everything we had looked at up until that point, all put together into this little object no more than 500 kilometers in diameter. Here we are now going on to Neptune, and we've learned that we're going to be surprised because we're coming into a system that we just simply don't understand, and almost anything that we learn about it, everything that we learn about it, is a surprise.
2 weeks before the close encounter with Neptune, the JPL engineers intensify their preparations for Voyager's flyby of the planet and its satellite worlds. Not only the planets, but also their moons reveal important information about the solar system.
In a sense, when we look at Jupiter and its satellites, or Saturn and its group of satellites, and the same for Uranus and Neptune, in some respects they behave as miniature solar systems in the way in which we think they form. They formed as a miniature example of a solar system, a large central body with others forming in orbit.
That could be just a
data that Voyager has collected may ultimately help us in understanding other solar systems.
Voyager's data is providing clues to how planets may have formed. The Neptune encounter could help to confirm the picture astronomers have of how our planetary system came into being. 4.5 billion years ago, the solar system was born from a giant cloud of gas and dust. Denser parts of the cloud attracted the surrounding material. Gravity held the cloud in orbit around the center. Clumps of matter within the disk began to form larger and larger particles. The inner core grew so hot that nuclear reactions began, and the sun, our star, was born. As the sun grew hotter, a solar wind swept the lighter material outwards. In the hot inner region, rocky materials formed into the Earth, Mars, Venus, and Mercury. In the cold outer region, ice and gas combine to form the cores of the giant outer planets. Beyond the planets, a cloud of cold material remained in orbit around the sun. Although too dark and too distant for us to see, astronomers are certain it must be there. In California's Owens Valley, radio telescopes search for signs of other worlds, disks of material around distant stars. Caltech's Anila Sargent and Cornell University's Steve Beckwith have discovered disks of gas around young stars. They suspect that at least one star, H.L. Tauri, 500 light years away, may be about to create a new solar system.
The one object we've really studied in depth is H.L. Tauri, and we chose this object because, in fact, over the past 10 years, there were other indications that the material surrounding this very young star was distributed not in a spherical envelope, but probably in some kind of elongated structure.
In the radio image of H.L. Tauri, Sargent and Beckwith have found an extended region they think is a disk, seen at an angle. Measurements of the motion in the disk show that gas moves in orbit around the star. Such a disk could be an early stage in the evolution of planets. H.L. Tauri is just one of many promising candidates for planetary formation that Sargent and Beckwith have found.
We don't just maintain this project at this observatory, we're doing it at several other telescopes. And so we had a rather large-scale project to look at about, I guess, 86, 90 of these T Tauri, these early solar-like stars, on a telescope in Spain called, the facility's called IRAM.
What we actually found was that out of the 86 stars we looked at IRAM, 40% of them had disks of gas and dust around them, which are very similar to the conditions thought to exist in the solar system immediately prior to the formation of our own planets.
Astronomers have long known that about half of all stars have stellar companions, most orbiting in pairs, called binary systems. Why do some stars have stellar companions while others do not? Sargent and Beckwith speculate that many stars may have formed planets instead.
One good possibility is that when stars form, their residual matter, which goes into a disk, or when it's falling down in, either makes another stellar companion, or else it makes a lot of small bodies, like planets, such as we see in our own solar system. If that's true, we might be able to guess that approximately half the stars in the sky have binary system or stellar companions, and the other half have planets. And if the other half have planets, it means that planets are very common in the galaxy and in the universe as a whole.
But I'd just like to check a few things that the site have to correct this, because we just feel better about the whole thing.
Astronomers are encouraged by the evidence that planets may be forming around young stars. But can they find planets already in existence? They would emit no light and no radio waves. Other methods of searching must be found. For Harvard astronomer and former off-road auto racer David Latham, the search for planets begins in his native eastern Massachusetts. 20 miles from Latham's home in Concord is the Harvard-Smithsonian Oak Ridge Observatory, where Latham has been surveying stars for planetary companions. Using an aging 60-inch telescope with an automated detector system, Latham believes he may have found a star with planets.
So how'd it go last night, Robert? Have any trouble with that high humidity?
We had a good run.
So that mean about 500 velocities this month?
Something like that.
Okay, I brought out the tape. I want to get the data transferred over. What we really want to know is how often stars, when they're forming,
decide that they're going to have a companion star, which happens a lot of the time, or instead they decide that they'd like to have a family of planets.
In the last 6 years or so, we've done more than 25,000 observations. And it's this steady flow of data that allows us to monitor stars to see if they have any unseen companions, judging from the very slight motions that we can detect with this instrument.
Latham searches for planets by looking for the gravitational tug that a planet exerts as it orbits the star. The star wobbles only slightly in response to the weak pull from the much smaller planet.
So when we look for the motion of a star in response to the pull of its companion, we're looking for very small motions. Which of the stars out there have these tiny motions in response to the pull of their planetary companions? Without any planning, we backed into a very convincing discovery of a low-mass companion to a star. We, quite by accident, noticed that one of them seemed discrepant. It was deviating from the values that we'd been measuring by about 500 meters per second. I want to see how bad this alignment problem is.
Latham's observations revealed a small wobble in the star, a back and forth motion from the gravitational pull of an unseen object in orbit around it.
And we went back and looked at all the observations, about 60 of them that we had accumulated, and lo and behold, we found an orbital solution that looked pretty good, but we sure didn't want to trust it.
Latham put the star, HD 114762, under constant surveillance. Astronomers at the telescope were instructed to observe it every night. Each night's data was immediately transferred by Latham from Oak Ridge to the Harvard-Smithsonian Center for Astrophysics in nearby Cambridge.
Hi, Bob.
All right.
Good present here from Oak Ridge.
Well, we'll see what we can do with it.
Within 3 months, the number of observations of HD 114762 tripled. Data from the telescope was fed into the Harvard computer, processed, and analyzed. The numbers supported the earlier observations. Something was making the star wobble.
So, have we found another planetary system around another star around HD 114762? Well, maybe. This object that we found could be as small as just about 10 times the mass of Jupiter, but remember, Jupiter's the biggest planet in our own solar system, and we're far, far away from seeing anything as small as the Earth. It's certainly not ruled out. The way to find out is to keep observing.
Yeah, I'd like to take a look at the data.
As David Latham searches for planets around distant stars, other astronomers strain to hear faint radio signals from the Voyager spacecraft at the edge of our solar system. On August 17, 1989, JPL prepares for its final planetary rendezvous with Neptune.
Right now, we're 7 days away from closest approach, and if you you can deal with that, you could talk about being 9 million miles away from Neptune, but, what does that really mean? If Neptune were the size of a basketball, okay, right now you'd be about 180 feet from the basketball. You'd be walking toward it at about 30 feet per day. So just during the last couple of days, you're going from seeing an object fairly remotely to getting incredibly close to it. We'll be getting pictures of Neptune essentially at arm's length. And the spacecraft itself will fly only about, on this scale, about 1.25 inches off the surface of it.
Neptune is, at the moment, the most distant planet from the sun, and it's dark out there. Something like 900 times fainter than the sunlight that we have here on the Earth. And that creates problems. It's like a photographer trying to take pictures when the available light is very low. The photographer can use a fill-in flash. We can't.
Well, it goes around the equator, all the way around.
A typical day would be in early looking at the photo products. Did they come out? Did they come out right?
Candy Hansen has the unusual role of interplanetary camera director. Her job is to allocate Voyager's imaging time among the competing needs of several teams of scientists.
And this image of the great dark spot came down
the middle of the night. Pass that one around.
Right on.
7 days before closest approach, pressures mount as overnight images must be analyzed before the daily 10 a.m. press conference.
Oh, am I first, or is that first?
Well, it didn't seem to matter. We had you first yesterday, and it didn't.
I couldn't make it.
For project scientist Ed Stone and imaging team leader Brad Smith, this is a week of discovery, decisions, and deadlines. As Voyager nears its target, the Neptune mission becomes the focus of worldwide attention.
La influencia terrestre que tiene la influencia emocional.
An army of 1,100 television, radio, and newspaper correspondents converge on JPL. Brad Smith and Ed Stone are tour guides on this journey to a brand new world.
Good morning. My colleagues in the imaging team are a bit tired, as might be expected, but they're also very excited, rather boisterous, because the images just keep getting better and better. Let's just look at some of the atmospheric images that have been received over the past day or so. You can have the first slide, please. It's a view of some of our favorite features on the atmosphere of Neptune.
New images reveal Neptune as a dynamic and stormy world. The planet is streaked by 1,400-mile-an-hour winds, the fastest in the solar system. A giant storm as large as the Earth is a major discovery. It is named the Great Dark Spot.
As we come into closest approach. It's this incredible acceleration of knowledge that you get all at once. At the same time, you have half the scientific community looking over your shoulder, and the press is looking over your shoulder, and everybody wants to know what it all really means.
Well, you just announced for. Does that mean that there are others that...
You're not allowed to ask us questions.
Yeah, you're not allowed to ask us things like that, but I think it's safe to say...
Find the ones you can't ask, and we'll try to not ask.
We will lose our jobs.
No, it's safe to say that there are a lot of features that we're seeing in the air, and we've been in a real panic in order to understand the orbits of the rings in order to target them. One of the things I became involved with are the looking for and identifying and characterizing what the ring system of Neptune was. And that's a process of rather tediously looking at the frames as you get closer and closer. And it turned out to pay off.
Voyager's first images showed incomplete rings, or ring arcs. Now, long exposure images reveal something more.
Continuous ring. Oh. And it goes all the way around.
Carolyn Porco, leader of the ring investigation, announces the finding.
Values for you yet, but as some of us suspected, we are now seeing continuous rings in the Neptune ring system.
That's a fantastic discovery. You know, it's the way these things pop out. Somebody comes running up to you and says, "Wow, look what we got!" You go in there. Wow, great, fantastic. We're getting incredible pictures. You probably all seen the ring movie images that came down this morning, and many of you I know have noticed that more than one ring could be seen even in the raw images, the so-called ring arcs.
The media expect these new images and discoveries to be explained and interpreted virtually on the spot.
Was that smooth today with the captions and...
Things went very smoothly today. My only complaint is the stuff that came from atmospheres where it was just cut and dry.
The most interesting science was coming in, and my team of scientists were wrapped up in that. I had to hold them back and direct their attention to the responsibilities of getting captions written, getting the science summarized.
Today. So you'll have the best color from either the stuff that came in this morning or the stuff that hits around at 3 o'clock.
Candy Hansen is our interface between the imaging teams and the Voyager project. We have a number of instruments, all wanting to look at different things, and there's only so much time and so much computer capability aboard the spacecraft, and so it's a competition. Candy has just gone in there and fought for us.
Looked at, and if it does even contain a piece of the south feature, I'd like to have at least a speaker slide made of that.
Voyager would send back to Earth more than 9,000 images. Each arrives as 640,000 dots, which are computed, processed, stretched, and enhanced to yield photographs. As Voyager closes in on Neptune, its cameras reveal a planet very much alive. Giant cloud features change in a matter of hours. One persistent feature is a small white cloud nicknamed the Scooter, which races around Neptune's southern pole. On the night of closest approach, Neptune's satellite, Triton, comes into view, bringing new images and new puzzles.
What is it? It's a crocodile of the solar system.
The thing about these encounters is that there is a very intense experience of discovery, much more intense than normal scientific activity, where if you make 1 or 2 discoveries a year, you really feel you have a very successful program. On these encounters, you make many discoveries every day.
Now Voyager must fly over Neptune to reach Triton.
The only way to fly close to both Neptune and Triton was to go over the north pole of Neptune, some 3,000 miles above the cloud tops, and then down to a close encounter 25,000 miles from the surface of Triton. In order to do that, though, we had to go very close to Neptune, and we had to penetrate the ring plane just outside where the ring arcs are.
The danger is, what are you going to find accumulated in the ring plane? The ring plane is where all the material tends to accumulate.
It's going to be an anxious moment because we're moving along at tens of kilometers per second relative to Neptune or anything that's in orbit around it. And all it takes is something the size of a BB or smaller to hit the spacecraft in a vulnerable place, and it's all over.
We go to the opening.
Yep.
We come to you.
Right.
You give us the distance and time. Okay. And we come back to you. You say a few words. We say, let's have examples of star occultations. Right? You want the tape then?
Yes.
Okay. Then we come back to you.
Rich Terrell trades his imaging team duties for a new role as NASA's broadcaster to the world of the dramatic ring plane crossing.
Okay, now
great.
still store, I've got
You've got this picture of the ring arc, and you've got that other picture of Triton.
Terrell begins broadcasting 2 hours before the ring crossing, which is scheduled to occur at 10 minutes past midnight.
I'm your host, Rich Terrell. At 10 p.m. Pacific Daylight Time, the spacecraft is 95,000 kilometers, or 58,000 miles, and speeding away from the planet at a speed of 55,000 miles per hour.
As Voyager follows its course toward the ring plane, members of the imaging team keep vigil in Building 264.
And we're starting a little bit early today because we have a special event about to occur. With us is Ed Stone, Voyager project scientist, and Don Gurnett, principal investigator of the plasma wave investigation. Comment on the ring plane crossing.
The data that we're receiving right now is being plotted here.
Voyager's progress is tracked by an instrument on the spacecraft called the Plasma Wave Science Experiment.
So the very most recent data is right there.
Mission scientists can watch as the graph registers tiny particles bombarding the spacecraft.
It's just dust, that is micron-sized, micrometer-sized particles. It will cause a lot of signal for Don's instrument, but it won't hurt the spacecraft at all. If there are BBs, on the other hand, that could be a very serious problem.
Well, it should have happened by now.
It's 59 right now. I don't know how good the prediction was. Ring plane crossing.
So, Candy, when do we know that?
Is that what you guys asked? Yeah, got 10 more minutes.
Why 10 more?
No, it was at 11:59.
In fact, you can see that peak right there. That is probably exactly the ring plane crossing where it goes up and reaches the peak.
What? It's better do a 90-degree turn.
It looks like it went down. And we're still receiving data, right? A sigh of relief.
Voyager's survival of the ring crossing is more than a celebration of another mission accomplishment. It is also the beginning of a farewell for a team that has shared a 12-year, 5 billion-mile journey.
I'm sitting here.
Now what we're waiting for is the approach to Triton, and that'll begin in 2.5 hours. And those will be the highest resolution images of Triton we've seen so far, very much better than what caused a considerable amount of excitement here 2 or 3 hours ago.
New images of Triton show surface features of the Earth-sized moon that appear to have been formed by winds.
You got a wind streak?
Oh, they're wind streaks, no question about
How
it.
can you have a wind streak with such a tenuous atmosphere, though?
Well, you get the winds to
Fall
blow.
migrations, you got to blow very hard.
You get the winds to blow fast enough.
Yeah, but do you calculate how fast it's got to blow in a several millibar atmosphere?
Obviously, it knows how fast to blow because it's certainly streaking that material out.
That's something else.
You have to just get right ballistic
As
wind.
views of Triton arrive, Voyager scientists are eager to know more about its atmosphere. For planetary geologist Larry Soderblom and satellite expert Torrance Johnson, evidence of an atmospheric haze may hint of a volatile world.
Then as we flew closer and closer, it was, the atmosphere was clear and we could see complex geologic detail. And so everyone was happy except for the atmospheric scientists that were hoping to see hazes. And then just as the cameras scanned over during one of the near encounter sequences to the horizon of Triton, there it was, a haze.
They're just perfect.
Do you see a limb haze? Come on, let's stretch it. Do you see a limb haze? Let's go check. Do you guys see a limb haze? When we looked at the limb, that is the edge of the Triton, against black space, we saw that there were clouds standing above the surface. We call that a limb haze. It doesn't completely surround the planet like a uniform cloud, but it's localized in certain regions.
Well, now that we got that,
Here we go. Here's some stretch.
I guess the last thing we have to figure out are these dark things, right?
The icy surface of this frigid world has few impact craters and shows evidence of extensive geological activity during its history. Huge volcanic calderas appear to have been flooded long ago by a lava of water. Triton, with its icy polar cap of frozen nitrogen and methane, is the coldest world yet visited in the solar system.
C'est extraordinaire. Et bon, il y a d'une part le moment historique qu'on est en train de vivre, tout le monde en est tout à fait conscient, et d'autre part, il y a des scientifiques qui s'accumulent et qui viennent les unes après les autres.
Carolyn, BBC, they want to know about rings. Triton hasn't stolen the whole show, baby.
International interest extends to the imaging team's Soviet member, Sasha Basilevsky, who ponders the chemical makeup of Triton's icy terrain.
Nitrogen, some people say that might be mixture of liquid of water with methanol. Methanol means something close to alcohol, something like of vodka.
Carolyn, we're going to go just with Triton this morning. No ring or atmosphere stuff.
That's
but
fine.
When the Triton images came in that night, it was clear that Triton was going to be the subject of the press conference as far as imaging was concerned. So we set to work about 3 o'clock in the morning, poring over the data, trying to put together some picture of what it all meant.
Triton leaves scientists with a wealth of information and new mysteries to explain. 10 a.m., Friday, August 25th. The International Press Corps gathers one last time to hear of Voyager's final encounter.
Well, as Ed has said, we have now seen Voyager's last planetary object, Triton, as the spacecraft begins its journey into interstellar space and that interstellar mission. And all we can say now is, wow, what a way to leave the solar system.
Voyager is sailing into interstellar space at nearly 1 million miles a day, free now to float forever through our galaxy of stars. The weekend after closest encounter with Neptune, the Voyager imaging team meets for a final farewell.
And I think we should have a show of hands. Who's here from that 1972 imaging team?
Oh. Come on, Brad, higher, higher.
Come on, Soda Bomb.
Way up here.
1972. Yay! And I'd like to salute the people who've been running the imaging team from then on, and I'd say it's the best way to run any NASA experiment, and I wish there'll be another one run like that.
From our leaders.
The next toast has got to be to Deputy Imaging Team Leader, who gets totally out of control up at the press briefings from time to time, but Larry's been with me from the beginning.
He has a
Great.
champagne model for every planet. All right, well, here's, I've got a...
This group of men and women helped create a special moment in history. Voyager gave us our closest look at faraway worlds.
For giving Brad a vacation. And keeping him out of our hair so we can set this up right so that so he could get the big bang out of it. Here's to Brad.
With Voyager, not only you feel close kinship with the spacecraft, but there are over 1,000 people that really made this encounter happen. You spend a lot of time with those people. In fact, a lot of times you spend more time with those people than you do with your own families. And over the last 10 years, you've gotten to know those personalities as well as the personalities of the spacecraft.
We got all the unimportant toasts over with first. Okay, here's the candy. We couldn't have done it without her.
The imaging team has shared life's milestones for a decade. Some have named their children after the planets and their moons. Others remember years past by Voyager's encounters. For some, Voyager is an inspiration for the future.
It'll be Christy's choice as to what she wants to do when she grows up, but she's at least going to grow up knowing about the planets and what they look like and what their names are, and that it's okay to be a woman and have a fun, exciting, scientific job. Yeah. Even though you miss Mommy at times. Yeah.
The real story is that if I really think about what's happened in the last few days, it's intellectually perhaps one of the most stimulating times of my life. Emotionally, it's one of the saddest. I've been here for the last 10 years. I've worked on this mission and always anticipated one encounter after the next, realizing they'd be fantastic, realizing that there'd be things totally unexpected. And it's over. We've done it. We've finished the first reconnaissance of the entire solar system. We've rewritten the textbooks. What do you do next?
Paris, France is Brad Smith's last stop in the journey to the edge of the solar system.
With the Voyager observations of Neptune now, there will be a need to produce maps. And the maps have to have names. So craters have to be named, features on Triton. The satellites themselves have to be named. And so there's a need right now to provide that nomenclature to the scientific community.
The Paris headquarters of the French Space Agency is host to this year's meeting of the Nomenclature Committee of the International Astronomical Union. These astronomers give names to the newfound features of our solar system.
Tuonela,
T-U-O-N-E-L-A, which is a Finnish sacred lake, which should be in there. Sacred sea.
This name is very popular in Russian culture from Greek.
Members represent the Soviet Union, Norway, France, and the United States.
In choosing names in the Neptune system, we try to maintain a self-consistent theme. For example, Neptune is the god of the sea. And the previously known satellites, Nereid and Triton, follow in that oceanic mythology.
Well, we're really doing two things, I guess. One is to assign names to the features that we've all agreed need names, but then the other thing we need to do...
We do not ever name features after religious leaders. Political leaders have to be dead about 1,000 years.
In terms of the discovery of Neptune. And
just now, it's the bicentennial of the Declaration of Human Rights. Not of the French Revolution, that's something different. French Revolution, even if it is the universe, but human rights, that is completely universal. And the symbol of human rights is three words: the liberty, equality, and the fraternity with brotherhood. See? And so my suggestion is the following, you see? And it's not the French, it's not something French, universal. So my suggestion will be the following. It's not national.
Astronomers do astronomy for different reasons. I personally am just interested in how everything came about, and in particular how we came about. And that means we need to try and understand if we're alone, or whether there are other solar systems.
The desire to know whether we are alone in the universe draws Brad Smith and Rich Terrell back to Chile each year in search of other solar systems. A stop at the seaside town of Coquimbo breaks the long journey to the observatory. Smith and Terrell never make the trip without paying their respects to an old friend, Mario.
Antes nunca estuve así enamorado, no sentí jamás esta sensación. La gente en las calles parece más
Mario, ¿cómo va?
Gracias al amor. Antes nunca estuve.
It was on an earlier trip to Chile in 1984 that Smith and Terrell took an intriguing picture of a star. The image suggested that planets may have formed around it. The star was Beta Pictoris.
Beta Pic is a fairly nearby star. It's only 50 light years away. That seems like an enormous distance. It takes light 50 years to travel there at 186,000 miles per second. But it turns out to be one of the nearest 1,000 or so stars in the solar neighborhood. That's a small number compared to the 100 or 200 billion stars in our galaxy. To give you an idea of how far that is, if you imagine our sun the size of a grain of salt, then the nearest stars to the sun would be about 7 miles away. Beta Pic, on the other hand, would be something like 80 or so miles away.
We have now looked at something of the order of 130, 150 stars, both in the northern hemisphere and down here in the southern hemisphere. But so far, we haven't found anything else like Beta Pictoris.
The challenge of detecting planets directly is that the material you're looking for is about 1 billion times fainter than the star and much, much closer. So it's buried in this enormous glare from the center star.
The problem of seeing planets in the glare of a distant star is a great challenge. But finding another planetary system would be an historic event in astronomy.
Well, that was a nice sunset. The seeing now is just as good as the night is clear. We'll be in good shape.
Looks like another good night.
It's a good night.
Okay, it looks pretty good. Looks like we might want to move.
The detection method Smith and Terrell use involves blocking the glare of the star's light to look for planets around it.
And what we've essentially done
with this mask is it's like when you look up at the sun and you put your thumb in front of the sun so you can look very close. We've done that in the telescope, creating, in a sense, a miniature eclipse. We've eclipsed the center light from this very, very bright star.
Smith and Terrell's original picture of Beta Pictoris seemed at first unexceptional. But computer processing revealed a slight extension in the image. Color coding showed the extension even more clearly. Smith and Terrell interpret this image as a disk of material around the star seen nearly edge-on. Other observations suggest that there is an empty region in the center of the disk, a hole that may have been cleared by the formation of planets there.
I think we ought to reobserve some of these. We saw these last year, but that was under pretty poor seeing conditions, and we can go much deeper if we use a bigger mask.
Yeah.
And we should take advantage of the seeing.
Well, we should do Beta Leonis again, and I think HR 5670, HR 5825, that was a really good candidate. HR 1998 would be good.
The search will continue until the day that astronomers find a star with planets. Until then, we can dream of other worlds, alien landscapes that may even harbor life.
Walking by someone's an astronomy office down in La Serena, and I saw a sign with a quote on it. I don't know who said this, but it said, "Hydrogen, a light, colorless, odorless gas, which given enough time, turns into people." And that's really what science has found. We, humankind, are a piece of the universe which has become self-aware. I think that science's goal now is to understand the universe. What we try to do is put that great puzzle together. The exciting thing that we found is that the processes that led to the evolution of life are fairly common.
We know what the chemicals are, that the elements that are responsible for life, and they're ubiquitous. They are everywhere. They are the most common elements and molecules in the universe. If you can get these materials together in the right environment, and by the right environment I mean a solid body, a planet, at just the right distance from its star. This is a natural process. This is chemical evolution. It's going to take place anyway. There's no way to stop it.
When you look at the numbers, the vast numbers of stars and potential sites out there for the evolution of life, you can't possibly deny that it can't be occurring in many, many places. And quite literally, there are more stars in the visible universe than there are grains of sand on all the beaches on this planet. Next time you're at the beach, run the sand through your fingers and try to imagine only one of those grains of sand containing a blue planet like the Earth. I mean, I think you'd have to be crazy to really believe we're the only civilization out here.
Monday night, David Attenborough traces the Amazon from its source in the Peruvian Andes to its huge coastal delta in Brazil. The Living Planet, Monday at 8 p.m. Now stay tuned for Reading Rainbow coming up next on TV 12.
The Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Video cassettes of the Astronomers and a complete set of educational materials are available from PBS Video. To order, call 1-800-222-5796 or write to the address on the screen.
This is PBS.
Luciano Pavarotti and Aprile Milo in Verdi's masterpiece of passion, politics, and prophecy. The Metropolitan Opera presents Un ballo in maschera, conducted by James Levine.
A Masked Ball from the Met, Friday night at 9 on TV 12. Saturday night, One Soldier's Story.
I'll shut you up. I'll find you.
The Pride of the Marines. Then, Steve McQueen on a mission of revenge. Nevada Smith, following the Pride of the Marines. Saturday night on TV 12.
Jubilee has your tickets to paradise. You and 3 companions will fly United Airlines for 6 exotic nights at the Hilton Hawaiian Village on Waikiki Beach. Enter the WHYY Jubilee of Prizes sweepstakes, and you could be relaxing in the tropical splendor of Hawaii.
Monday night,
Vacation time.
another family tale from Gene Shepherd.
I gotta go.
Ollie Hupnoodle's Haven of Bliss. Monday night at 9:30 on TV 12. Sunday afternoon, take off on a European vacation with Travels. London, Paris, Burgundy, Germany, and Austria. A spectacular 5-hour tour, barging through Europe on Travels. Sunday afternoon beginning at 2 on TV 12.
Join thousands of Americans for the National Memorial Day Concert, a salute to Operation Desert Storm and to all men and women who have given their lives in service to our country. Live from the West Lawn of the United States Capitol.
Sunday evening at 7:30 here on TV 12. We're TV 12.
Reading Rainbow is made possible by grants from the Corporation for Public Broadcasting. This station and other public television stations. And B. Dalton, bookseller, who urges children and parents everywhere to follow the Reading Rainbow. B. Dalton is committed to literacy and hopes that in your house, reading is a family affair.
Butterfly in the sky, I can go twice as high. Take a look, it's in a book, a reading rainbow. I can go anywhere, friends to know and ways to grow, a reading rainbow. I can be anything. Take a look, it's in a book, a reading rainbow. A reading rainbow. A reading rainbow.
Balloons here. Balloons. Balloons.
Hi there. What a beautiful day to be out in the park. I love it.
Ice cream. Ice cream.
Miss!
All right, what can I do for you?
Now, let's see. I'll have chocolate.
Okay.
Or maybe a strawberry. No, wait.
All right.
A vanilla. Yeah, definitely a vanilla with 2 scoops, okay?
Okay.
And some of those sprinkles, those rainbow sprinkles there.
All righty.
Great.
There we go. And thank you.
Thank you.
Ice cream.
I've been waiting all day for this.
Yeah.